computer. Okay, so if you've got two devices, make sure that you're not listening to audio on both of them, because then we'll get feedback. And can everybody hear me?
Yes.
Kind of.
Yes.
Okay, this is the best my voice is going to get today. So I've been dealing with laryngitis starting last week, like Tuesday of last week, and this is as good as it's going to get. I've been taking care of it for the last 6 days, hoping that this is as good, that it would get better than this, but this is as good as it's going to be. But at least I can make a go. So
Take breaks.
yes, lots of breaks and
Water.
lots of actually tea with honey.
Ah,
Lots of that. Tea with honey. Okay, so good morning, and I know people are still showing up. So I'm Scott. My call sign, which will make sense, is N7JI as we get toward the end of the class. I'm in Eugene, Oregon. We are recording this, yay. And the goal of this class is I've figured something out. This is like the 40th or 41st one of these that I've done.
Oh,
Some of them, a lot, probably half have been in person and half have been online. And what I've learned by teaching classes is that we have kind of like two blobs. The one blob is all the theory behind the stuff that you're learning. The other blob is the fact that you have to take a test. And that's why one of the things that I sent out was, when I sent out all the information, I said, one of the most important things you can do is study and practice, because as much as I may be able to teach you everything I know, I mean, I've been at this for almost 40 years. As much as may be able to teach you everything I know, I still can't help you. I still can't make you pass a test. Ultimately, that ends up being something that comes out of your ability to study and practice and go in and be confident and take a test. So, Bruce, you got echo there. So, my wife, who got her license about 5 years ago, got her license so that I wouldn't nag her anymore. She has no technical. I mean, she's actually quite a good technical person, but she has no real technical interest. She's never been through an engineering class. She's doesn't. I mean, she took physics. She had to. She basically understands some electrical stuff, but is certainly not an expert at it. But she's good at taking exams, and the nice thing about this is that the question pool from which every exam is drawn is about 400 questions total. And every exam gets built with a certain number of questions of certain types from that question pool. And so people start to think, oh, all the technical stuff, I'm never going to be able to do it. You know what? If you go through and you practice every question from every section, one section at a time, and you have seen every single one of those questions, because that's really the only way to do, like, the rules and regulations and things like that, is to go through and practice it. It's just like taking a driver's exam, the driver's written test. You can take a driver's written test never having driven before, right? What it does is it gives you the permission to go and actually drive, right? But it doesn't mean that you're an expert. It doesn't mean that you know everything. It just means that you can take a test and you can pass a test. My goal is to get you to that point where you're comfortable taking a test. But the other part of my goal, because I'm a strong believer in, education and understanding the stuff that you're actually studying, is that you're going to actually understand some of the stuff that you're studying. And it will not only make it easier to take this test and feel confident in the first place, but what it will do is hopefully spur you on to say, oh, when I actually get my license, when I actually build something, when I actually start operating, I kind of understand what's going on. And oh, it's not that hard for me to go and start studying for the next exam because I have a basic understanding now. So you have 3 levels of license. You have technician general, and extra. You're going for the technician. Is there anybody here who's been taking a lot of practice exams and is just killing it? And you know it if you're just killing it. Anyone? Nobody?
Taking a lot, but I'm not killing them.
Okay. If you're killing it, you'll know. My 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 um my limit for killing it is if you're getting 85% or higher every single time. And to be totally honest, if you're going to pass and you're going to guarantee that you're going to pass, that's the way to guarantee that you're going to pass. There's no limit on the number of practice exams you can take. If you are taking practice exams and you're getting 85% or higher every single time, you're going to pass. And you're going to be confident doing so. It's going to be really easy. If you are in that boat and you've been doing that, then studying for the general exam is going to be really easy because there's about a 60% overlap in material between the technician and the general. And the reason I know that is because I know of people who have gone through and aced the technician exam and they try the general exam, never having seen it before, and they get 50 to 60%.
Wow.
So in the interest of me saving my voice a little bit, I'm going to turn it over to all of you guys. And so I'm going to start with, okay, so I'm going to give you each about 30 seconds. Keep an eye on your time. About 30 seconds to introduce yourself, name, where you are, and what you do and how you ended up interested in this. And then you're going to look around the screen and pick the next person. And again, that's why I said, if you can, please change your name to like your name and your state so that we have a little bit of uniqueness in who we're calling out. Okay, so I'm going to start with Don MC.
I am 57 years old, 56 years old.
Don't have to tell your age, but okay.
Oh, okay. Sorry.
No, it's fine. Just, we don't have to get too personal. Yeah.
I'm retired. I have a total of 7 children.
Oh, wow.
I don't know how many grandkids at this point. I'm retired. And I got interested because my biological dad was interested. And I've been practicing and trying to test since 2018. And something's not clicking somewhere.
All right, pick the next person.
Sue,
Me.
yes.
Good morning, everyone. Thank you, Scott. Thanks, Scott, for doing this. I have, well, first, I'm Sue, and I live in between San Francisco and San Jose in the Bay Area. I'm here because I've wanted to do this for 10 years, and I'm finally doing it. And it's because of my brother, who was very active in the Florence, Oregon amateur radio. And I'm really happy to be here. I'm a retired public school teacher, and I also am doing this because I have really fun grandsons, and I want them to become licensed ham radio operators. So I'm going to do it first, and I will pick there. I don't see the name, but it's KC9IEE, a young gentleman right in the middle.
Hello.
Hi.
name's Nicholas from Illinois. I got interested in this because of my dad. The KC9IE, that's his call sign. I'm sorry if I don't know how to change it on Zoom. So,
That's all right.
I just did it.
oh, thank you. Got interested in this because my dad has a giant cabinet full of this stuff. And I just started looking through it one day and just saw all of it. He said I could do it one day, and yeah, that's about it.
Makes it a lot easier when you don't have to go buy stuff.
Yeah.
All right, pick the next one.
Chris from Oregon, I think.
Hello. So yeah, my name is Chris. I'm in Oregon. I've been using radios since about 2013 through search and rescue with volunteering. It's always been for training or emergency situations, so I've never needed an actual ham license. Recently, someone on my team was talking about Scott and his class and about all the new technology in radio. And so that really kind of spurred my interest, and I want to learn more about it and get a license so I can use it in my off time. And let's go with Doug Oil, or Doug from Oil City, Pennsylvania.
Hi, everyone. Yep, like he said, I'm from Oil City, Pennsylvania. Grew up here, retired Air Force vet. I've been interested in radios since childhood. Started off with CB. My dad was into the ham. He tried to get me licensed, but I was a little tyke, so I didn't know all the technical questions real good and all that. So just got interested in it again, and looking forward to making new contacts.
All right, pick the next one.
Let's see here. How about Bruce K?
You're muted.
Oh,
Bruce, you're muted. Yep, you're still muted.
I'm gonna try to go to another person.
Yeah, go to another person. We'll get Bruce going.
Oh, okay. Let's see here. How about Howard from Florida?
Okay. Good morning, everybody. I'm from Florida, obviously. I got interested in this because my dad was a ham radio operator, and he tried to get me interested into it for years, but I was too busy working or raising family. So, but I decided I got some time now and I need a new hobby. And so something that's not going to cost me a lot of money, because I've had other hobbies that cost me a lot of money. But anyway,
spend as much as you need to.
yeah.
All right, and Bruce is alive again, right?
I'm alive.
And Bruce, remember I said you'd hear at least one other story like yours?
Yeah, you're right. Well, I'm Bruce K from Florida, Palm Beach County. And hey, I've been a nerd since I was 12 years old when I built my first transistor radio. And I just put this on hold for the rest of my life. And now I'm back. So here I am.
All right, pick somebody.
Oh, I got to pick somebody. Okay.
You got to pick somebody. That's how we get to know each other.
Yes. Sam. Oh, I'm sorry. It's not Sam. It's Seth. I put my glasses on. Hey, Seth. There you go. Seth is muted, it looks like.
Yeah, let me unmute myself there. I'm Seth. I'm from Oregon currently, but I've also lived in Pennsylvania for quite a bit of my life, like Doug. Also a similar story. Ham radio seemed cool when I was a kid, and then life gets in the way, and here I am years later, and just looking for something to help me get a little motivated. Sometimes the self-study is not as successful when you got other things going on. So joining a class, meeting other people seemed like a good plan.
Cool.
Go
Next.
down the list. And, I'm going to pick Robert from Sproul, Oregon.
And I don't know where that is.
I'm Robert Sproul. Um, so yeah, so I live in Oregon currently. I've well traveled, retired Navy, now Social Security retired. Was kind of looking for something to do, but then I got involved in the local community emergency response type stuff, and they need a ham operator in our neighborhood. So
Cool.
it's kind of my motivation. I've been I've been technically adept for a long time. My dad worked for the county government installing radios for the sheriff's office. So I used to go hang out in his shop all the time, and some of it kind of rubbed off. So anyway, that's kind of my deal. Formerly of Alaska, formerly of Colorado, grew up in Redwood City, California. If we have any
Yay.
California, yay.
All right, Robert, where do you want to send it?
Let's see. Let's go with Teresa from Alabama.
You are correct. Good. My name is Teresa. I'm from Alabama, 66 years old, retired acute care nurse practitioner, involved in all kinds of community emergency response organizations and groups. I've been being beaten by some of the other members who are experienced hams, and it's time when and if things get bad, we're going to be able to need to be able to communicate. And that seems to be the number one thing that I hear throughout the community organizations is how bad communication between organizations and how difficult it is to get things organized because of a lack of communication. And if we need each other or need outside news, we're going to need comms. So I need to know it.
Okay. Teresa, pick someone.
Becky, Alabama.
Hello, everyone. I am Becky, and I am a retired medical lab tech, and I took an interest in ham radio maybe the last couple of years. Last summer, I went to the first Ham Fest in Huntsville. I really enjoyed it, and I decided to partake in it. I wanted to take it last year, but I got involved with CERT responder instead of ham. And so I've been trying to read the big red book, and it's very technical, and I have a lot to learn, and I'm thankful and grateful that I'm here. And let's see, choose somebody. How about Linda in Oregon?
Hello.
Good morning.
Good morning. My name is Linda, and I am from Oregon. I became interested in this as my father was a logger, and he had bugs, and then there were CBs, and I've been interested in this a long time, but I know nothing. And that big red book that was just mentioned, it sounds like I need to find that and get that. Scott was listed in a forum that I belong to, and I was like, okay, this is my chance. Partially retired, got some back issues, got a couple of grandkids. The son is a first responder, so I kind of feel like that this might be a good thing for me to try. So let's go.
Who do you want to pick?
How about Doug in Oil City?
We already did that. Already did it.
I can't tell. How do you know?
I'm just remembering.
Okay. Well, let's see.
You want me to pick?
Yeah, go for it.
Okay, how
please.
about Naomi Kelly? And some people might not have audio. So how about Rose Eddington?
All right. Hello, everyone. I'm a college kid. I am a mathematics student at Portland State University. And I found out about this class through our aerospace program, our little aerospace club that we have on campus. Shout out to Andrew, who I'm picking next. Sorry, Andrew.
Go ahead, Andrew.
Hey, I'm Andrew. I'm the faculty advisor for the Portland State Aerospace Society and a technician class, but trying to upgrade to general or extra. And hi, Scott. And Scott, thank
Hey.
you so much as always for doing this. And I picked Toto because I think I know who Toto is.
You might know Toto.
Hello. Yeah, I'm Toto. I'm from Oregon. I actually already took my license, I mean my technician in general, but I'm retaking the class to learn a little bit more material. We learn a little bit. And I originally got interested in ham radio because of a family friend.
So are you in Oregon or Massachusetts or New Hampshire right now?
I'm in Oregon right now. Yeah, but I go to boarding school in Massachusetts or in New Hampshire. Yeah, but so yeah. And for next person, how about Dawn from Oregon?
I went through the class last March, and if anybody can pass it through Scott, if I can't, anybody can. So,
Thank you.
Enjoyed it. I got my technician's license, and I've been through what we call Tour de France here, and was operating for that with that. And I also did my field day last Saturday, and just loved it. And I'm just looking and want to get more information so I can get through the general and then into my technician or into my extra license. And let's see. Is it Kasia? Kaisa?
Kaisa.
I'm Kaisa. I first got interested actually because I watched the movie Contact with Jodie Foster when I was really little, and she had a ham radio, but I didn't know anybody who did it, so I never got a chance to learn. And then I started going to the University of Oregon. I
Ducks.
and then, and then one of the ham radio club members introduced me to Scott, and so I learned about this class, and so I can finally fulfill a childhood dream.
Oh.
There you go.
And then I will choose Bruce and Evander. I think I'm saying it right.
Good morning. Can you hear me?
Yes.
I'm Bruce. And first of all, I'd like to say that this is the second time I'm doing this class. About a year ago, a little more than a year ago, I took this class with Scott, who is a former customer of mine. I'm up in Portland. And I managed to pass my technician and general at the same sitting, which was really satisfying. And I'll add to that that it's not hard to do. And Scott hit the nail on the head when he first introduced it. You have to run through those sample exams on your phone, on your computer, whatever it is. You got to go over those over and over and over again, put in half an hour a day, and you'll have it down in 2 weeks. And that's the way to do it. And the stuff that he's going to give us is just background. It really helps. So it's all good. It's a great program. I invited my son Evander, grandson. Sorry. Thank you, Scott. Thank you. Evander, I'll let you introduce yourself in a moment, but yeah, he was showing some interest. I showed him my shack. I took him to field day the other weekend, and I'm pretty excited that he's showing some interest. So I'll let him introduce himself next.
My name's Evander and I'm 14.
You're just 14.
Yeah.
Like yesterday or
Yeah.
something.
So Evander, where do your interests lie in school? Out of curiosity.
I don't know.
Favorite class?
I don't have any.
No, okay.
Well, I'm gonna jump in on that, Evander, because you're a computer kid. Like so many kids, they're doing games and computers. They're on their computers a lot or on their phones, right? And that's something you do. That's important to you. And the cool thing about ham radio today is that the computer and the radio are tightly connected together. And so anybody that is interested in computers or spends time on computers is going to find all kinds of really fun things to do with the computer and their radio. So that's the one thing I'll add to that. Okay, I guess I'll pick somebody else. Who has been? I have the same problem.
Daniel S. has been waiting patiently.
I was just going to say I landed on him, so go ahead, Daniel.
Hey, good morning, everybody. My name is Daniel. I am a student at Portland State University, where I found out that this class was going on. My background in radio is when I was in high school, I was at an Explorer post, where we used like VHF radios up in the hills a lot off of repeaters, a little bit of like UHF police radio too. That was a lot of fun. That's where I first got interested in it. We had some hams who were volunteers who showed us about how that stuff worked. At one point, I was helping out with the ham club W6YX at Stanford University for a few years. But I never got my actual ham license because I was just kind of doing grunt work. So I'm excited to do some studying and get a license so I can do some learning about this stuff on my own and also help out with some RF related projects here at Portland State. Thank you.
Go Andrew and go Josh. How about Mia?
Hello.
Yep.
Yeah. My name's Mia. I'm from San Antonio, Texas. I'm a student at Case Western Reserve University, though.
Go
And
Case.
I'm getting into this because I have a handful of friends in Radio Club, one of whom is on our Baja team, and our Baja team needs people to have their licenses to communicate with our driver. So,
Case
yeah.
is a good club. I'm active in the CARP program, and I've seen them at every meeting. They're awesome.
Really?
Yeah.
Oh, that's cool. Yeah, I suppose I'll choose Naomi next.
See if Naomi comes back. Nope. Okay. How about Frankie L? Well, you're unmuted, but I can't hear you.
Hi, my name is
There we
Frankie.
go.
I live in Connecticut, and I think that this I want to be. I think going to this one, and my mom got her license. It's
Very cool. Okay. How about Dwayne in North Carolina?
Hey, good morning, everybody. My name is Dwayne. I'm in Wilmington, North Carolina, out here on the coast. 30-year first responder, retired as a fire captain 3 years ago. Still work for the Department of Army as a civilian doing telecommunication stuff, radio repair, telephone repair. Always wanted to get the ham license and well, finally just decided to dive in.
Cool.
And let's go to Eddie in San Antonio, Florida.
Hello, good morning. My name is Eddie, and I started early in my career and in my schooling, graduated an engineer in electronics, and the test was mandatory, and I never took it. I disappointed my instructor. So here I am in another chapter of my life, and I am ready to undertake it and get moving with it. And that's about it.
Can I ask what year that was?
That was in 1982.
Can you still contact your instructor?
No, he has passed.
Because I thought maybe you could finally get the credit, and he'd be happy.
It was a mandatory thing, and he was really disappointed. I did really well in class and successful in life after that, thanks to his education.
All right, next. How about Ed I?
Hi, I'm Ed Ivory here in Portland, Oregon at Portland State University. I had to look it up, but I got my technician back in 2018 by doing the ham study. I think it was before they even had an app for your phone in 2018, and it was just clicking through all those test bank questions on the website. That was sort of the beginning of my undergrad program in 2018, and it's taken until 6 months ago, I guess, to finish my bachelor's in mechanical engineering, where now I am the program manager for the electronics prototyping lab at Portland State, and I am sort of a sheep in wolf's clothing, if you will, there as a mechanical engineer. I bring a little bit different perspective to that program, and I'm here primarily because of Andrew again. He works right next door, so it's yeah, it's great to be here. Thank you. We'll go with Christian K if you haven't gone yet.
Hi, my name's Christian, and I'm here from Florence, Oregon. My growing interest has been from seeing all the other people around here, well, just doing it in general. Seeing a lot of my teachers doing it as well, picking up satellite data, just looking at stuff. And well, yeah, that's my basic introduction for me. Who else?
Let's see if
Who else is-
Naomi Kelly came back. Nope, still no audio. How about John and Mason?
Hi, my name's John. I've always kind of been interested in ham radio, but just never really pursued getting a license or anything until just recently my son, said he was interested into it. So we decided to do this together. And so we came across your class, and so we thought we'd take it together and make a go of it.
Hi, I'm Mason. I too was interested in it when I was little, and we saw that this class was here, so we decided, you know what, let's take it. So, yeah.
So here we are.
Yeah.
Let's see, who else is
there anybody else who we haven't gotten to yet? Speak up.
Me.
Okay, Lewis. Was it Lewis?
Yeah.
Take it away,
Hi.
Lewis.
Good morning. My name is Lewis. I work in disaster recovery. I recently volunteered an ODART exercise on the coast, and I saw how cool the wind links and all that other stuff is, and so I want to pursue ham radio.
Excellent. Okay, was there anyone else?
Yes, hello. My name
There
is
we go.
Max. I'm a mechanical engineer at Portland State University, and Andrew keeps on recommending getting ham radio license every year, and so I finally decided to go ahead and try taking a class.
Yay.
And I'll call on Art, and then I think the only person left is someone with their phone number.
Well, hello everybody. Yeah, so I got the technician license, end of December 23, beginning of January 24. So I've been kind of having fun, joining some group in the air. But I'm very happy, to do this refresher, this class. So thank you, Scott. There is so much to learn. I'm trying to get my son to get involved with this, but we'll see how much progress I do. Thank you. And the other guy with the phone, it's me. It's my phone number.
Oh, okay.
Just in case. So just please ignore that.
Okay, so I think we got everyone.
Thank you.
Anyone
I don't
else?
know if we got Mia.
Nope.
No, we got Mia.
Yep. Anyone else?
So Naomi's able to come in.
I think so, yeah.
Okay.
Okay, well, so being that this is a radio class, the first thing we're going to do is discuss something that has nothing exactly to do with radio at all. So tell me if everybody recognizes what this thing is. What is that? What is that?
A circle.
A circle, okay. And now what we're going to do is we're going to draw a line like this and draw a line like this. And so now that we have this circle, we have split it into 4 quadrants. They're numbered 1, 2, 3, and 4. Right? Okay, how many degrees are there in a circle? I told you this is a very...
360.
Yeah, this is going to be a very interactive class. So 360 degrees. Okay, and by definition, our 0 line is right here. That's 0 degrees between the first and fourth quadrant. And when we add angle, we go counterclockwise. No, I don't know why we go counterclockwise. But there are
the rules.
Yeah, that's right. There's a rule. Okay, so there are 4 points on this circle that are of extreme interest. One is right here at the top, and that's at 90 degrees. One is all the way over here on the left. That's at 180 degrees. And then we continue around. This is 270 degrees. And then we keep going, and we are at 360 degrees, which is also known as 0, is it not?
Yes.
We're at the same point. Okay, this is really important. Because does it matter if we go around the circle twice? Do we still end up right here? How about if we go around the opposite direction 10 times?
Same thing.
We still end up exactly where we are. That's right. Okay, so now what we're going to do is say that we're going to draw a picture. We're going to draw a line, and this represents, notice, nice and grassy green. So this is the surface of the Earth. And we're going to start at 0 degrees. And then we're going to go around the circle. And we're going to start at 0. And we're going to say how far above or below ground are we when we get to certain interesting points. So the first interesting point we get to is going to be 90 degrees. If we say that this circle has a radius of 1, this is the unit circle, how far above ground are we at that point? When we get up to the very top, we're 1 unit above ground. How about when we get to 180 degrees, which is all the way at the left?
2.
We are not. We're back on the surface.
Oh, that is correct.
So, okay. How about at 270 degrees?
-1.
-1. We are 1 unit underground. How about at 360 degrees?
0.
0. Okay. So now what we're going to do is we're going to connect the dots. We can do this. But as you can see, that doesn't really work, does it? Because if you look at the actual position above the ground as this angle changes, it goes up quickly and then increases slowly until it gets to the top. When we start connecting these dots together, we get a graph that looks like this. Anyone know what that's called?
Wave.
Sine wave.
Yep.
So a sine wave is generated by the act of basically sitting on a circle and riding up and down. The function, how far above or below this axis, this is known as the sine. S-I-N or S-I-N-E. Right? So it's the actual function is the S-I-N-E. It's represented by the letters S-I-N. So, and I'm not going to answer that. Okay. So now we can also draw a different version of this circle. Or I should say it's really the same version of the circle, but we're going to go and look at it in a different way. So now we're going to draw this vertical line. We're going to make it a bright blue line. So here's our bright blue line. So now, instead of that first one, we are interested in how far left or right of that blue line are we? So if we start at 0, which is that dot on the right, how far, and if we define this as positive and this is negative, what is our distance from that blue line when we're all the way at the right-hand side?
180.
+1.
+1. So we start up here. Okay. How about when we wrap around to the top?
0.
We are on the blue line. That's right. How about when we're over here at the left?
+2.
We're -1. We went left of the line. How about at 270?
0.
Okay. And how about add 360?
+1.
All the way back to there. Okay. We can connect the dots. Okay. Now, what's important to note here is that because this is a circle, what can we do with it?
We could turn.
We can keep going because actually there's no beginning and no end, is there? This has no beginning and no end. How about the pink line? Does that have a beginning or an end?
No.
Nope. This blue line that we just drew is called a cosine wave. This is represented by COS. The pink one was the SIN. So you may be thinking, okay, somebody's got feedback and I can't tell who it is. Okay, let's try that. Okay, I think we're good. So we have a cosine wave and we have a sine wave. Now, so everybody's probably thinking, well, this is kind of dumb. This is a radio class. Why are we bothering to do this? Well, it turns out that this is the most fundamental thing that we do in radio is we generate sine waves. And so the other interesting thing about this is what do you notice is different between the sine wave and the cosine wave? This is an excellent opportunity to demonstrate something about this.
90 degrees of phase.
Yeah, the only thing that's really different is that if we start with the pink and we make the blue, the way to make the blue out of the pink is that we take this and we shift it 90 degrees backwards. We could also take the blue one and we could shift it 90 degrees forward. So really a sine and a cosine, because they both come from a circle and going around the circle, they are just each other, but shifted by 90 degrees. And when we say 90 degrees, that means that it is 1/4 of the circle. They're shifted by 1/4 of the way around the circle. Okay, now there are some really important things about sine waves. And the reason this is the fundamental reason why I've drawn this. And you might say, well, okay, I didn't know we were going to be learning trigonometry. Yeah, okay, you didn't know you were going to be learning trigonometry today or going back to do trig. But it's important because now we just introduced something called phase. Phase is very important. We can alter the phase of something and we can cause it to shift in position. Now, the other thing that does, in addition to altering it in position, is it alters it in time. Because we can take this phase and say, okay, what we're going to do now is look at this circle that we drew, and we're going to look at it as a merry-go-round from above. Right? Has everybody ever been on a merry-go-round in the playground?
Yes.
Yes. Okay. So let's say that you get on at 0 degrees on the merry-go-round. So this, all the way on the right-hand side, is the entry point to the merry-go-round. So if somebody were to look at you from the side and say, okay, well, I'm going to be on this merry-go-round, and they were to map out where you are on the merry-go-round, they would see that in a certain period of time, you would be at the first position. At a certain time, you'd be at the second position, and then the third position and the fourth position, and then you go around and around and around and around. How long does it take to go around this merry-go-round?
Depends on the speed.
That's right. It depends on the speed. And in more importantly, what that period has a name, big letter T. This is our period, and this is measured in seconds. So that's the first part. That's how long it takes to go around. Now, we can also say, if we were to normalize something and say, we're going to say, how many times does something happen in a second? Well, if it takes 1 second to go all the way around, how many times does it take to spin around in 1 second?
One.
That's right. That's known as a frequency. In this case, it'd be 1 revolution per second. How about if you went 10 times as fast?
10.
Yep. And then you'd probably get nauseous and puke over the side. Or you get thrown off the edge. So what does this mean? It means that period and frequency are inversely proportional to each other. Now, let's say that instead of going 10 revolutions per second, we were to go 100 revolutions per second.
Oh.
Well, okay, that would mean you go around something 100 times every second in this case, right? This is something that we don't typically want to do, but for the case of argument, for the sake of argument, we're going to write it that way. And what I'm going to do now is hopefully go to, is it okay with everybody if I erase this?
Scott,
Okay.
what program are you using to do all this drawing?
This is just a Zoom, a classic whiteboard. And an app and a decent pencil. Okay, so now we've gone around the circle. Around and around and around and around until we got nauseous doing it. We have a couple of fundamental things. We have our period, seconds. And we have our frequency, which is things that happen per second. Well, this things per second, that has a name.
Hertz.
We call that a Hertz, named after Heinrich Hertz. So we can now say, okay, if I have this that spins around 1,000,000 times per second,
Megas.
Right? So we can now say this is 1,000,000. It has a frequency of 1,000,000 hertz. We can also write that as 1 megahertz, because mega means 1,000,000. We'll get to units as well. So now what we're going to be able to do is we're going to move on to the next logical step of doing this. We're going to, in addition to having this merry-go-round, we're going to now make it a bicycle wheel, right? Because we can do that. It's magical. We can call it anything we want. And we can put an LED on that bicycle wheel because LEDs are really small now. And if we were to spin this LED, or spin the bicycle wheel, I'll draw the spokes. It's a very simple bike wheel. If we were to spin this around, what would we see in a dark room?
That light going in circles.
That light going in circles, exactly. Okay. At what frequency would it go around?
Depends on the speed.
Depends on the speed. That's right. Okay. Well, now what we're going to do is we're going to take this bike wheel and we're going to do a little visualization thing on it. We're going to take this bike wheel and we're going to turn it sideways. In a dark room, what are you going to see with that LED? What pattern is it going to make?
Straight line.
Yeah, we just rotated this on its side. So we're just looking at it edge on. And what are we going to see the LED doing?
Straight line.
It's going to be going up and then it's going to go down. It's going to go down to the bottom and back up. It's just going to be making a vertical line, right? With what frequency?
Depends on the speed again.
It depends on the speed that the thing is turning. Exactly. All right, but now we're going to add another axis of movement.
Well, no, right angle.
Yeah, we're going to add another axis of movement. So somebody's going to take this bicycle wheel, which is moving up and down, and move it horizontally. So what pattern is that LED going to make now?
A spiral.
It's going to go up. Yep. It's going to go down. It's going to kind of look like a spiral. But what are we actually going to see?
Sine wave.
A sine wave. What do you know? We're going to see a sine wave. But what is going to affect how long, how big that sine wave is? There's now two things. What's the first thing?
Speed of the wheel.
Speed of the wheel.
Time.
Distance of horizontal movement.
And distance of movement. And velocity of movement. So we have the rotary speed of the wheel, right? We have the rotating speed of the wheel. And we also have how fast it's moving sideways.
Isn't there one more variable though, Scott?
Which one?
The diameter of the wheel.
Yeah, but we just assume that, you know, that the diameter of the wheel will change how far up and down it goes. But it's not going to change the length of the wave. Okay, so that changes the translation speed of the wheel. And we have two things that are coming into play now. We have the rotary speed and the translational speed. And we measure the rotary speed in, what did we say?
Hertz.
Hertz, which is rotation, in this case, rotations per second. And how about this translation speed? What is that measured in? If you're walking, what do you measure that in?
Meters per second.
Meters per second or feet per second or miles per hour. For the convenience of this, we're going to say meters per second because it turns out that meters per second and rotations per second, what do they have in common? Do they both have a per second?
Yes.
Which means we can do cool stuff with those. We can divide them. So we can take our translation speed in meters per second and divide it by our rotary speed in essentially rotations per second. And those will cancel out. Now what do we get? What's left here?
Distance per rotation.
Meters per rotation. We get a distance per rotation. Well, that sounds to me like if we have a distance that's covered, it will make that pattern, does it not? If we have one rotation, it will make one full wave because that's what that rotating wheel does. We just established that. And now we just took it and we moved it at a certain speed. And by dividing one by the other, what we get is meters per rotation. Well, rotation we can replace in this case by a wave. So now we have meters per wave. Or length.
Wavelength.
Length per wave. This is known as the wavelength. And it is dependent upon the speed of the thing and the frequency of the thing. Interesting, right? Okay, so now we've been able to take something that's a spinning wheel that's generating a sine wave, and turn it on its side and then move it and generate a brand new sine wave whose wavelength is now determined by the frequency in hertz and how fast the thing is moving through space. That generates something called a wavelength. And what that means is we now have this thing we call a wavelength, which we use the Greek letter lambda, and we measure it in meters, is equal to speed, which we're going to use our letter V, and frequency, F. And we can verify this by saying, okay, this is meters per second, and this is rotations per second or waves per second. Make sure we did it right. Meters per wave is equal to meters per second divided by waves per second. So we did it right. So now we have a brand new formula. The formula is wavelength is equal to speed divided by the frequency. Measure this in meters. This is meters per second, and this is hertz. We can rewrite this. V is equal to F lambda. This is a really important equation, right? This relates speed and frequency to wavelength. So let's take a simple example. We're going to take a velocity and we're going to assume, let's first assume a sound wave traveling through the air. Sound wave traveling through the air is about 330 meters per second. That's about the speed of sound at sea level. And we're going to now take a frequency of 440 hertz. Any musicians here? Do you know what a 440 hertz is? What note?
A.
That's your tuning A. That's right. That's your tuning A. Okay. So we're going to use our formula and say we have our V and we have our frequency. So which one do we not know? We don't know the wavelength. So we're going to figure out what the wavelength is. So we're going to just plug it in. Say lambda is equal to 330 divided by 440 is equal to
3/4.
Oh, that's cool.
that is the physical wavelength of an A at 440. It is 75 centimeters long as it's traveling through the air. That determines, okay, so what are some important things that determines?
Antenna.
No, not that.
No.
This is, remember, we're talking sound. So let's say that you have a column of air and you resonate it down at the bottom. This will make a standing wave. What happens if the column is too long? What will happen to the note?
Will dissipate.
No, if the column's too long, it will resonate at a lower frequency. So if you're playing a musical instrument and your tone is too low, I've played musical instruments my whole life. I play the flute. If your flute pitch is too low, what do you do with it?
Make it shorter.
Make it shorter. That's right. If your pitch is too high, what do you do?
Make it longer.
Make it longer. That's right. So the wavelength, and let's say this is a guitar string. you want to make it resonate at a different frequency, you can change its tension as well. You can't do that with an air column, but you can do that with a guitar string. So there you go. This is our physical manifestation of frequency and wavelength. So now we're going to take this
No.
physical. Go ahead.
I'm trying to write as you go and I can't keep up.
It is, I am recording it.
And that means I can look at it later.
Mm-hmm.
So I can pay attention and stop writing. Okay, done.
Yeah. Okay. So the next thing we're going to do is we're going to take this thing that's moving through space and it's making out a pattern that looks like this. So the speed of sound is 330 meters per second. But now we're going to take something else. We're going to take light. This 330 meters per second doesn't apply anymore. How fast does light travel?
186,000 miles per hour.
Yes, no, per second.
Per second, rather, right?
Except that we really can't work with that in miles. But we can do 300 million meters per second, which is about the speed of light. 300 million meters per second in free space. So if we have a frequency and a wavelength, that formula V equals F lambda still applies. What do you know? It still applies. Because that just represents something with a frequency, something with a wavelength, and something moving at a velocity. Well, in this particular case, we can replace V with the letter C, which is the speed of light, which is 300 million meters per second. And we can use F. So we're going to say 1 hertz times lambda in meters. This is 300 million is equal to 1 times lambda, or lambda is equal to 300 million meters. So if we had a light wave or just any wave that was making light and it had a frequency of 1 hertz, how long would its wavelength be?
300 million.
300 million meters. How far is 300 million meters? That's 300,000 kilometers. That's like the Earth to the moon. That would be the wavelength. That this one wave, as it traveled through space, making that pattern, would be about the distance from the Earth to the moon. Okay, well, what did we do? What did we say about musical instruments? That a musical instrument, in order to make a certain tone, has to be a certain size, right? Can you think of too many practical purposes or uses to make something that is a piece of wire 300 million meters long? Because I can't. I can't. So what we're going to do instead is we're going to make a wire or make our wave again. I don't know why I keep drawing that little blob. Here's our wave. And how fast is this wave moving at the speed of light?
300,000 meters per second.
300 million meters per second.
Sorry, million.
That's how fast this thing is traveling. Okay. So now at 300 million meters per second, we are going to say that instead this has a frequency of 100 megahertz. This is being generated by a spinning wheel going around how many times per second?
100 million.
100 million times per second. And then we rotate on its side so that it looks like this straight up and down. And then we move it at 300 million meters per second. So we're going to do our little formula again. V is equal to F times lambda. In this case, it's C equals F lambda, which is 100 million times wavelength. And C in this case is 300 million. Okay. What is lambda?
3
What's
meters.
3 meters? 300 million divided by 100 million. 3 meters. Now, how big is 3 meters? About 10 feet. Well, guess what? Can we make something like a piece of wire that's 10 feet long?
Yeah, an antenna.
Yeah, it's called an antenna. So what this means is that if we could pick something that's moving at the speed of light and oscillate it that fast, in this case, 100 million times per second, we can actually generate a wave that is 3 meters long. Well, if we went really fast, that would be one thing. If we went really slow, that'd be another thing. What we're going to do instead is we're going to do this. Can everybody see this nice picture? Everyone see that okay? Okay. So notice what we have at the top. We have frequency, and at the bottom we have wavelength.
Don't worry about it.
And what you'll see is that if you multiply at the top, 300 million hertz or 300 megahertz times 1 meter, you get 300 million meters per second. So this is between the top and the bottom. These are the relationships between frequency and wavelength. As the frequency changes, that light that we're using, moving at the speed of light, has different names. These are all forms of electromagnetic radiation, and they are part of the electromagnetic spectrum. Notice we have way over here on the right-hand side. Does anyone recognize that stuff?
Don't worry about it.
Ultraviolet and infrared.
Yeah, but how about those things? How about those colored bands?
Is that
Visible light.
That's visible light. Yeah. So
Roy G. Biv.
Roy G. Biv, that's right. And then above that, we have ultraviolet, we have X-rays, we have cosmic rays, gamma rays. And then as we go longer in wavelength, what do we have? Infrared. And then we have near infrared, far infrared. But then what do we get to?
Microwave.
Microwaves. Okay. And that's like 100 millimeters to 1 millimeter. And then what do we get to?
Radio waves.
All this stuff. Everything lower than 300 gigahertz in frequency is considered radio waves. But what is the difference between a radio wave and blue light? What's the only difference?
The frequency.
The frequency, which leads to the wavelength. What's the only difference between red light and purple light?
The wavelength.
The wavelength and frequency, exactly. They're all just the same thing. They have different energies, and they have different frequencies, and they have different wavelengths. They all travel how fast?
Speed of light.
Because they're all the same thing. Okay, so last thing before we take a break.
Bless you.
Okay, so we are going to have obviously something that moves this way, because we said we're going to have our bicycle wheel, which goes like this, moving in this direction. Well, as it turns out, this is a very special bicycle wheel.
Both ways.
Because we do this and we do this. So this is an isometric view of a three-dimensional system. All of these axes are actually perpendicular to each other. So we have a perpendicular axis system. We call this the x-axis. We call the y-axis, and we call this the z-axis. That's a three-dimensional system. We live in space. We have 3 dimensions that we frequently deal with, right? We have our x, our y, and our z. X we usually think of, x and y we think of as along the ground. Z we think of as up in the air, but if we turn it, so long as if everybody holds up their right hand and sticks out their 3 fingers, use your thumb. Your thumb is your x-axis, your index finger is your y-axis, and your middle finger is the z-axis. And if you hold them all perpendicular to each other, that's how you create an axis, a system of axes in free space with 3 dimensions. So if we have a sine wave that goes like this along this axis, that is known as our electric field. Perpendicular to it, we have this.
Pretty good drawing that perspective there, Scott.
Thank you. This is our magnetic field. And a photon that is moving through space, a photon is a particle of light. So this is our direction of our photon. Will generate an electric field and a magnetic field. So will an electron, which is moving through space. What do you notice about the electric field and the magnetic field? They always go through 0 at
Same
the
spot.
same spot. And when one goes up, the other one goes up. When one goes down, the other one goes negative. And they're always in phase with each other as they're traveling through space. This wave has a very special name. This is an electromagnetic wave. The electric field is also known as the E field. And no, I don't know why exactly, but the magnetic field is known as the H field. They're always perpendicular, and they're always perpendicular to the to the movement of energy, which is the photon moving through space. And the way to do it, if you ever get into trouble, is you hold up your hand, make sure it's the right hand. And yes, it can also be the B field. That's true. It's either B or H, depending on, I usually think of it as the E field, the H field, but E, H, and direction of motion. So at any point in time, your thumb is the direction it's moving. And if your E and H fields, they're just going up and down, you can rotate them 90 degrees. You can also have them so that as they're traveling, they're continually spinning. Yeah, it's pretty cool. But if you try it with your left hand, it doesn't work. You end up being wrong. All right, so now we've covered the basis of electromagnetics. And you know what? I'm going to put one more thing on the board. This is your cheat sheet for figuring out frequency and wavelength. Right there. That's a terrible circle. Draw it again. Ooh, I could make it a real circle. Look at that. I can do a real circle. Isn't that pretty? Okay, so 300 F and lambda. So the reason that we made it 300, that represents the speed of light. Why do we not put 300 million up there? What do we usually measure our frequency in radio? Megahertz, which has a million that is implicit in the name. So what that means is we can not do the extra zeros. So what we do here is, let's say we want to know for a 1 megahertz wave, a frequency of 1 megahertz, how long of a wavelength would this make? Well, we don't know the wavelength right here. We cross that out. So we have our wavelength is equal to 300. Notice we have this division bar here, divided by frequency. 300 divided by F is equal to 300 meters. So a 1 megahertz wave, or 1 megahertz frequency would make a wave 300 meters long. How long is 300 meters?
About 1,000 feet.
About 1,000 feet. Okay, so here's one more thing before we go take a break. Now, this is approximately what we call AM radio. When you see 1,000 on your dial, that's actually in kilohertz, which is also 1 megahertz, which means that the wavelength is about 1,000 feet. FM radio is a frequency of about 100 megahertz. And we're going to plug that in, cross this out again. 300 divided by F is equal to 3 meters.
3 meters, yeah.
Which is about 10 feet. Now, how in the world do you suspect you could have a single device that would receive both of those, considering that when you start looking at wavelengths and antennas, your antenna has to typically be a half of a wavelength long, maybe a quarter, depending on what it is. But if this is a wavelength of 1,000 feet, let's say you can get away with a quarter of a wavelength. What's a quarter of 1,000 feet?
250.
250 feet. Okay. Where do you find those when you drive around the neighborhood?
Towers.
That's right. This is an AM radio tower. Those do exist. Okay. Now, those are typically out in the middle of the field. They're super, super tall because they have to be. How about an FM radio tower, FM radio antenna? What's a quarter wavelength at 10 feet? How long is a quarter wavelength at 10 feet? 2.5 feet long. 2.5 feet long.
Yeah.
So a quarter wavelength at that, this is about 2.5 feet. Where can you find that?
Car.
On your car, that's right. So an FM transmitting antenna for an FM station really only has to be about 2.5 feet long. So now here's the real question. How do you receive both of these with your car? On your car radio? Well, your car antenna looks like this, and it's about 2.5 feet long. That's for your FM radio. But now, what do you do for the AM radio, considering you need about 250 feet of wire? Has anyone ever broken an AM radio apart?
Yeah.
What do you find inside it?
A lot of little transformers.
You also find this thing called a ferrite bar, which is a piece which is wrapped with a very fine wire. Wrapped around that bar is a lot of very fine wire, which makes an AM receiving antenna. And you don't really worry too much about it being inside your car and being terribly inefficient, because somewhere somebody's got a 250-foot radio tower transmitting signals at 50,000 watts. So now here's another question. Has anyone ever taken a listen to AM and FM radio during the day and night? What do you notice on FM radio? Does it matter if it's day or night?
No.
Okay. How about AM radio?
Yes.
What's happening?
It gets clearer at night.
Atmospherics.
Yeah, why?
Ionosphere.
So what's happening during the day?
You're able to bounce it off the ionosphere.
Yes, so here's AM radio during the day. And so here's the layers of the ionosphere, D, E, F. During the day, this layer builds up really heavily. Your AM signals go up into the ionosphere and they get absorbed. At night, that dissipates. And what happens to your AM radio signals?
Fades in and out.
Yeah, but they're able to get up higher because
farther.
that absorbing layer is not there anymore. So at night, you're able to hear AM radio stations long distances. Like, here's your car. During the day, you can't. With FM always essentially punctures the atmosphere, no matter what frequency you're on, because it's at 100 megahertz. The key is that whether it's called AM or FM is not important. The key is that this is at 1 megahertz and FM is at 100 megahertz. And this is something that's called propagation, which we're going to get to soon. All right, everybody ready for a 5-minute break? You know, let's make it a 10-minute break. I got to make tea. All right, so what time is it now? It is 9:52, so 10:02.
Scott.
Hey.
Hey, it's Lynn Brill. Danny and I joined you a little late. I want to apologize for that. There was a miss on, probably my miss, but on what timeline you were on.
Wow.
Because Google argued with me.
Google was wrong.
Sorry about that.
Google was wrong.
Google was very wrong.
Glad to see you. Glad you made it.
How do you said that we'll be able to access this to review the first part?
Yep.
Okay.
Yeah, I'm gonna when it's done converting afterwards, I post it on YouTube and send out the link to everybody. So
Oh,
so long
thank
as I so long as I have your registration, as long as I have your email, you get that.
Yep. So thank you
Right.
very much.
All right, I think it's time to get going again. Yep, it is. Rock and roll, everybody. Okay, so we are now we have established what a radio what a wave is, what a radio wave is, because once again, we have this electromagnetic spectrum. It has radio waves, it has microwaves, it has infrared waves, ultraviolet, it has X-rays, gamma rays. So, okay, very importantly here, there are three ranges that we look at and we give names to. Now, okay, there's microwave, but we're not going to deal with that one too much. We have this right here. We have the high frequency HF, VHF, which is very high frequency, and ultra high frequency, which is UHF. The limits for these are 3 to 30 megahertz for HF, 300 to 30 to 300 for VHF, 300 to 3000 for UHF. Those are internationally recognized limits for what are called HF, VHF, and UHF. So when you used to watch channel 6 that was on VHF, it is somewhere in this VHF range. When you used to watch channel 13, that was VHF. Channel 14 is in UHF. And it turns out that we do not have exclusive access to all these frequencies, nor does anybody else. And that's actually really important to realize, because I don't remember if I sent this out to everybody or not, but there's something called, let's see. Oh, there we go. The NTIA frequency chart. I did send it out. Did anybody by any chance suffer through taking a look at this chart? Did anyone look at this?
What is that?
That is the allocate. This is the allocation of frequencies in the United States.
Yeah, I don't remember seeing this myself at all.
This was in that this was in that information packet. This is the allocation chart of all the radio frequencies in the United States. And notice how they're broken out. This band covers from 3 up to come on. Three up to 30. The next one covers 30 to 300. And the next one down below calls 300 to 3000. Now, it's important to note that even though they take up the same amount of space on this chart, what is the total amount of spectrum in the HF band? What is that equal to? How many megahertz is that? Between 3 and 30. How many megahertz is that?
27.
27. How about between 30 and 300?
270. Okay.
How about between 300 and 3000?
2,700.
Each one of those has 10 times more space in it than the previous one. And when I say more space, it really comes down to the amount of bandwidth available on a particular band. And why is that important? And this is just open to the floor. Why do you think that's important?
Frequency allocation.
Frequency allocation. Does everyone like having a cell phone? Does everyone like being able to have a really high bandwidth for being able to download stuff and stream while they're walking around the neighborhood? Everyone like that?
Of course.
Okay, so let's say that you need 100 megahertz of bandwidth. In order to do that, you actually have to take your signal and have it spread out 50 megahertz in both directions for that to work. Look at the 3 to 30 megahertz HF band. How many megahertz are there available on that band total between 3 and 30?
27.
27. Well, we just said that if you want 100 megabits of bandwidth, let's say it fills up plus and minus 50 megahertz on this picture. Clearly, it's not going to be there.
Right.
Let's look at VHF. 30 to 300. How many megahertz is that? That's 270. You take up most of this, most of that area. So between 30 and 300, between 300 and 3000, however, you've got 2700 megahertz available, which means that for your cell carrier to be able to provide you the kind of performance that you want, they have to be able to use certain frequencies at which those kind of bandwidths, the amount of space on this chart that they take up, are available. And those fall in usually even above 1 megahertz. So those are like 1.4 megahertz, 1.8. And you can see if we zoom in on all of these, sometimes there are multiple different groups that use them. As you get further down, it gets even more crowded.
What are the typical cell phone frequencies, Scott?
Between 1 and 2 gigahertz.
Okay.
But then you start looking at like this. Notice this inter-satellite, space research, Earth satellite,
they're
broadcasting satellite. They're all sharing frequencies. Now, fortunately, at those frequencies, those typically travel in straight lines, which means that there's a fair amount of sharing that you can do where people don't interfere with each other. You have very small antennas and very high gain, high directionality, which is why it's not a lot of fun for just sending a signal off somewhere and seeing where it ends up, because you're looking at, so let's say you have a wavelength that is, we might as well get into some antennas here. Let's say you have so we're gonna pick a particular band. We're gonna do our 300 F and lambda, and we're gonna pick the 10-meter band, which is actually 28 megahertz. So at 28 megahertz, our wavelength is about 11.5 meters long. That's about 11.5 meters long, or about 35 feet. So in order to make an antenna that is functional at a given frequency, you would basically take two of the 0 points
I have
like
a
that.
10-meter antenna in my attic. I'll
Yep.
show it later.
So you would basically take two of these endpoints where this current is going to be 0. That would be called a half wave antenna because it's a half a wave long. This is the fundamental antenna. That's the basis for most antenna designs. And this would be about 16.5 feet long.
Which is exactly what I have in the attic.
Yep, and it works quite well. And so you don't need the second half. In fact, the second half of the antenna kind of just gets in the way. So your antenna looks like that.
I have exactly that in my attic right now, Scott.
Mm-hmm. So this is your wire. It's about 16.5 feet long. Now, the reason for what we're going to do now is we're going to say, okay, let's instead pick something in the microwave range, which has a frequency of 3000 megahertz. This has a wavelength of 10 centimeters. How long is 10 centimeters?
30 feet. About 30 feet.
Yeah, it's about the length of your middle finger. It's like 4 inches. That's the total wavelength. And your antenna actually only has to be half of that.
2 inches.
So about 2 inches long. So, and now we start getting into other things. So now we're going to deal with, let's make our antenna again. And here's our antenna. I don't know why it keeps drawing that blob. So here's our piece of wire, because every wire is an antenna, and every antenna is made of a piece of wire. Every piece of wire can function as an antenna, very important. This is a half wavelength long. It's split in the center. We'll just draw it like that. Total length of a half wavelength. This has a pattern when it's launching waves into space that look like this. It's called a broadside pattern. It makes kind of a donut shape around the wire. Now, the problem, of course, is what if you want to talk to somebody like way over here and the pattern goes that way and that way? What if you want to talk to somebody way over here? What do?
Rotate it.
You turn it, yeah. But this is already, and we went with something small. This is already 16 and a half feet long.
Well, you go vertical.
Yeah, well, you may not be able to. You may have to put up another antenna or build something that you can rotate. Now, so it also turns out that frequencies and wavelengths in this particular range, when they get up into the ionosphere, so we're going to cover that right now a little bit, D, E, and F layer. Those signals, when they get up into the ionosphere, they can refract back down to Earth. Essentially, they bend. So you have the ability for that to, at least come into play. But instead, let's take a look at microwaves, which have a wavelength of 10 centimeters. Right? So we determined that our same dipole antenna, because it doesn't care. It doesn't care other than to be the right size at a given frequency. So if I have a wavelength that's 10 centimeters long, how long should my half wave antenna be? If this is a half wave, how many centimeters?
5 centimeters.
Okay, which is about 2 inches total. This is about 2 inches long. Here's my wave. That is a perfectly good antenna for this particular frequency. 2 inches long.
Yeah.
If you look at if anyone here has like a Wi-Fi access point, you might find an antenna sticking on the back of it that's about 2 or 3 inches long. That's what it's built for. Okay, but what's interesting about this is how hard would it be to change the position of that antenna? What do you think?
Not easy.
Well, it's only 2 inches long. You could do anything you want with it. I mean, and it would work great. I could rotate it like this. I could do this with it. I could do this with it. I could put it up on the roof. It's only 2 inches long.
You could use a dish.
You could use a dish, right? Well, we're getting to that. So let's say that we now have our 2 inch long antenna, and we want to make this so that it's more directional in this way. We can actually add, here's our feed point. We can actually add parasitic elements that are longer in the back and shorter in the front, which give you something called gain, which we're going to get to in the forward direction. And the benefit of doing this is that they give you a pattern instead of looking like this, which is the donut. They give you a pattern that looks like a tiny little thing back here and a lot of energy in the forward direction. And this is known as gain. And the benefit of that is that if there's somebody in a different direction that you don't really care to talk to, you just turn it the other way. If there is somebody in another direction that you care to talk to, let's say your antenna is shaped like this, and the person you want to talk to is over here. But your antenna elements are only 2 inches long, and the whole thing is only 7 inches long. What do you do with the antenna?
Point it.
You just rotate it. Yeah. So there are certain advantages to being able to do that. Now, this antenna, this frequency is not going to be a lot of fun when you're just looking for random people to talk to. Why is that?
Many people have it.
Yeah, because as soon as you're pointed somewhere, you're ignoring everything else. So, and if you're aiming up into space, what's one of the primary uses for this kind of antenna?
Satellite communication.
Satellite communications. The reason being that if we draw our atmosphere again, we draw our D, E, and F layers, it passes right on through. So all of these radio frequencies have very, very different purposes, and they pass through the ionosphere in completely different ways.
This also worked very well for direction finding.
It does. Exactly right. Okay, so now we're going to draw a basic antenna for a particular frequency. So our frequency, we said we're actually going to pick one. We're going to take 146 megahertz. Now, this actually, I picked that number for a very specific reason.
Radio.
Did everybody get this? I should have, did everybody get a copy of this? I should have sent that out with your information packet as part of that zip file.
I don't think I got a zip file. I don't remember it.
Okay, because it would have had the book in it.
Book?
Yeah.
Didn't come through on mine.
You got it in the email.
Really? Okay.
Yeah, this one was the band plan update one from 2020.
Yep. It has the book. It has everything in it. It was
Yeah,
like,
we have it.
okay.
Hey, I guess
So-
I'll look back because I don't think I got anything like that.
If you got the welcome to ham radio class email, it should have been at the very bottom as an
Might be
attachment.
one I didn't see it.
Okay.
Okay, I'll go
right.
back and look.
Okay, so
On mine,
notice
it was the email from June 15th from welcome to July 1st through 3rd ham radio class. I thought I didn't get it originally myself either, but then going back through the emails, it was on a materials.zip.
Okay, I'll look it back.
Okay.
But
Okay,
Scott, I
so-
didn't get my email until late because you didn't get my text, which is how I originally tried to communicate with you. So I guess maybe I got an email and I just didn't scroll down far enough.
Okay. So everybody notice that we now have these bands. These bands are actually a part of these bands. Let me see. Hold on. Let me make sure I can pull that up. Okay, here we go. Let's why are you not playing nicely? Oh, hiding. Okay. Okay. So those frequency bands are actually contained within this giant morass of frequencies that we have that make up the entire frequency spectrum. These bands right here, can everybody see that? These amateur radio bands are subset of all of these.
Subset, okay.
We exist. Notice we have this thing called over here. There we go. That teal color that says amateur right there.
Yes.
We also have amateur satellite. If we look over here and we look for these teal colored areas, we'll see. Oh, that's our 3.5 to 4 megahertz band. That's called 75 and 80 meters. If we look over at our band plan, we will find 3.5 to 4 megahertz. Oh, look, it's the 80 and 75 meter band. If we find this band that says 50 to 54 megahertz, we come back over here. 50 to 54. What is that known as?
6 meters.
That's 6 meters. Okay. Does anybody here, has anyone here like had a license like way back in the 50s and 60s? Just out of curiosity.
No.
No? Okay. Anyone? Nobody? Okay. So notice, did anyone here live in a, did anyone here have the experience of watching Channel 2 or Channel 3 when they were kids?
Yep.
Did any of you have a ham radio operator in the neighborhood? Did any of you ever get interfered with where Channel 2 and Channel 3 were completely wiped out?
Mm-hmm.
Can anybody see why that might have happened looking at this chart? Anyone see anything?
The low end of the broadcast band intersects or bumps up into the upper end of the 6 meter band.
That's exactly right. And what
Is
would
that
happen
power?
is, what would happen is if there was a ham in the neighborhood, that ham, even if their signal was really clean, it could overload a TV station or a TV receiver that was watching, let's say, Channel 2 or Channel 3. Isn't that cool?
It's cool that we don't have to worry about that as much.
It is, isn't it? And the other thing that's cool is that we learned something at that point for those who were involved in that, called filtering. And what people would do is they would put on TV low pass filters, band pass filters and low pass filters, which would filter out the broadcast band on the transmitter and filter out the ham band on the receiver on the TV so that they didn't interfere with each other. But as you can see, this is the giant sandbox, and this is our sections of the sandbox.
A lot of competition for the airwaves.
Yes, that's true. And so if we look at this chart and we see that the lower on the chart it is, the higher the frequency goes, which do you think are the most coveted frequencies for all of these super high bandwidth applications that everybody seems to love now?
Internet.
Yeah, like internet over radio and stuff. What are people going to really, what are people clamoring for? More bandwidth,
5G.
right? 5G. Well, what do you see up here at like 75 gigahertz? What do you see right there? Amateur
allocation.
satellite. Okay, so let's take a look
Okay.
at another one of those teals. 5.6 to 5.9 over here on the left. Notice it says amateur satellite. Here's another one at 10 gigahertz. These are very, very big bandwidth allocations, are they not?
Mhm.
This right here is 10 gigahertz to 10.45 gigahertz. This is
Oh.
450 megahertz of spectrum. That is more spectrum than on the entire VHF band. That is more space than on the entire VHF band, which only has 270 megahertz in that one little swath. So, how much does AT&T, for instance, pay to use those frequencies to deliver bandwidth to its customers?
A lot.
How much do we pay to experiment on those frequencies?
A lot.
No, we don't.
Almost nothing.
We pay nothing.
Oh, I thought we paid pretty much.
We pay nothing. So somebody goes to Congress or the FCC and says, hey, we want these frequencies. Do you guys see a problem with this?
Absolutely.
Who's got the access?
Whoever has the money.
That's exactly right. So there is the only group out there that is, and this is my plug for the American Radio Relay League, ARRL, the only group out there that has Congress and the FCC's ear is the ARRL. I strongly support them. I'm a field services volunteer, and when you get your license, personally, I'm a big supporter. I'd love to see everybody become a member of ARRL. Here's ARRL. One of the big things that ARRL does is go to Congress and lobby for us. And so I think it was said that they have about a $3.5 million annual lobbying budget. And that's largely from member dues. Going there on our behalf and making sure that all those frequencies that we don't pay for, but we show some tangible benefit by using for other people, stays available to us.
3.5 million is not that much money.
3.5 million you can go through in a very, very short time.
And I'm a little worried about the U.S. Supreme Court decision just this week.
Mm-hmm. Yeah. So part of if you look at why ham radio exists, one of the core purposes is being able to develop new technologies and essentially give them away. Right? This is it's a very altruistic thing to do. Another thing we do is we use our frequencies to provide emergency communications, which is why a lot of you are here. Right? Well, if we don't have access to those frequencies, how good a job can we do?
Yeah.
So that's why I'm a big supporter of ARRL, and I'm a big, even if you don't agree with everything that ARRL does, I'm a big supporter of membership in the organization, if only for that purpose. I mean, there are plenty of others, but anyway, that's my soapbox.
It's well over 100 years old.
Yeah. And it's got 160,000 members, which sounds like a lot, except that there are 750,000 hams in the United States.
Wow.
So why is it only 20%? Why is when everybody gets the benefit? All right. Okay, continuing on. We're back into antennas, and we're gonna show that frequency chart again, and we're gonna say, okay, so we picked 146 megahertz. We call our bands colloquially.
A lot of the questions on the test relate to some of the topics and things that he's showing us here.
That's why we're doing it. Colloquially, we refer to our frequency bands by the wavelength in meters. So we could say this is the 146 megahertz band. We actually just say this is the 2-meter band because the wavelength is approximately 2 meters long. So we're going to pick an antenna for 146 megahertz. Right there, 146 megahertz. And we're going to share our picture again, and we're going to draw our 3 dots that time. So here's our wave, and it has a frequency of, oh, that is terrible. There we go. A frequency of 146 megahertz, which means it's making that full pattern how many times every second?
146 times. 146,000 million.
146 million times every second. But it's also traveling at 300 million meters per second. So we're going to do our conversion thing, 300, F, and lambda. And what do we know? We know the frequency, and we don't know the wavelength, so we cross that out. 300 divided by F, equal to 300 divided by 146 is equal to approximately 2.05 meters. Well, okay, it makes sense that it's called the 2-meter band, right? Wavelength is 2.05 meters. That makes sense.
638.
So now what we're going to do with this is we're going to once again say that we're going to make a half wave antenna. We're going to make an antenna that's half as long as the full wave. And this comes back to some stuff that we're going to do very shortly in basic electrical theory. What is an antenna typically made of, everyone?
Wire.
Wire. What is wire made of?
Copper.
Copper. And what's inside an atom?
Proton.
Yeah, protons, neutrons, and electrons. Okay. Current is the flow of electrons. Well, if you have an end of a piece of wire and you're looking for something to flow, so here's a piece of wire, and an electron comes in this way and it has nowhere to go, how much current do you have right here? You have to have 0. That's how we can get away with doing this and making our wire a half wave long. So our wire is a half of a wave long. At 2.05 meters, this translates to 1.025 meters. That's a half wave.
3.5 feet.
About 3.5 feet. Well, except that we have to take 95% just because the thing exists in the real world. And it ends up being about
4 feet.
Yeah, 0.98 meters. So that would be just about 3.3 feet long. If we were to make this, each one of these is about 19.5 inches. This one's 19.5 inches. And we feed this right there in the middle. That would be a half wavelength antenna for the 2-meter band. And this is at the core of all kinds of different antennas. I mean, you can be as creative as you want, which is why some people really love antennas. For instance, let's see, you can make a 2-meter, I'm going to pull up a picture, tape measure Yagi. Anyone ever done any direction finding? It's when you go and you hunt for a hidden transmitter somewhere in the field. Can everyone see this picture? What do we have there? What does that look like? It's called a tape measure Yagi. What is that? The element in the center is a half wave dipole. And what's that made of?
Tape measure.
It's made of a tape measure. Yeah. The longer element in the back, this is known as the reflector. This one's known as the director, and it's directional in the forward direction. Since it's easily rotatable and portable, you can carry it around and aim it wherever you want and go find the transmitter that you're looking for. As it turns out, yeah.
So most of the Aggies I've seen, the directors are shorter than the what's the driven one called? The driven
Reflector.
No, the driven element's the driven element. Director's going to be shorter. There we go.
So, okay, that looks better. So
yeah, this one looks better. I think the other one, the angle was a little weird.
Yeah, the reflector is the longest one.
Yes.
And the director is the shortest.
The shortest one. Yep.
Okay.
So this is actually pointed down at the floor. This is going to have a pattern that is aimed toward the floor.
Right.
Of course, you wouldn't normally use it like that, but you know, I've built many of these. You can build one of these with. Does anyone have a broken tape measure in their toolbox?
Who doesn't?
Yeah, it doesn't retract anymore. You just have to make sure you don't cut yourself.
I do.
These things are incredibly easy and very, very incredibly easy to make and completely functional. And what's really cool is because the conductors are big enough, you can actually use them as transmitting antennas too.
And they roll up.
And they roll up. Yeah. They roll up and they fold really well. So The other thing you can do with it, if you want to go a little bit further, is you can do something called a J-pole antenna. A J-pole is an antenna that is vertical. So you can, and it's typically flexible. See, and it's what's cool is all these pictures are going to make sense now. And notice that it's a half wavelength long. Essentially, this is an end-fed half wavelength antenna. But what's cool about it is that because it's fed off of the end and there's absolutely nothing special about it, what it allows you to do is make it out of flexible cable. This can be just like a single piece of wire or TV twin lead or your open wire feeder or 450 ohm. And you can take one of these, make it, and
J-pole.
yeah, roll it up in your pocket.
What's it do?
It's a
You can-
band. It's a 2 meter and 440 centimeter antenna.
That's the antenna?
Yeah, that's what he just described.
Oh.
Yep.
Oh, I thought he was talking about something about a roller.
He did that too.
Yeah. So there's this one, if it's made of copper and welded, that's called a copper cactus for obvious reasons. You can also make it so that it's much lower power, but completely portable. So you can pack it in your bag. I take one when I travel. It rides in my suitcase. And when I get to my hotel room, I just unroll it. I hang it from a window, like a window curtain or something. The 95% rule is actually because of capacitance and inductance of the materials, which we're going to get to.
Quick question.
Yeah.
So I have a J-pole in my hand. I was just showing it to Andrew, but it has 3.
Well, you got to show it to everybody now.
Oh, fine.
Come on, don't be selfish.
Okay, here we go. It's long.
Mm-hmm.
So this one has 3 elements.
Right.
So one of them's, this is a dual band
Yep.
J-pole, right? So it's
Yep.
440 or the 70 centimeter band, and 146, which is the 2 meter band, is
Mm-hmm.
the longer one. What is the shorty in the middle?
Matching stub.
Ah,
It's for impedance matching.
okay.
We're going to get to impedance also.
So that's a J-pole.
That's a J-pole. So there's all kinds. Antennas are where you can be most creative. And if anything works and you've designed it electrically correct, it'll work great. All right. So the last thing we're going to do before we get to the electronics is I'm going to draw this yellow blob in the sky. Anyone have a name for that? The sun. Okay, good. And now I'm going to draw the earth over here. And I'm going to put some blue skies around it. Okay. So what comes out of the sun? Let's hear it.
Electromagnetic waves.
Okay, that's good. So you have EM waves. What else?
Plasma.
Light. Radiation.
Yeah, okay. Radiation counts as part of electromagnetic waves. What else?
Photons.
We have lots of particles. Photons are part of those. They're also part of the electromagnetic waves. Photons are kind of like both. They live in both worlds. You could have electrons. You could have magnetic fields. Right? The sun is basically makes a mess. So what makes it to Earth, which is of interest to us, are these electromagnetic waves for the most part. What different frequencies make it to Earth? Well, we have light. We have visible light, otherwise we'd be very dark. We have ultraviolet, we have infrared, we have X-rays, and we have lots of radio, actually. The sun makes a lot of radio waves. Okay, so what happens to the light when it gets to our atmosphere?
We see it.
We can see it, yeah. But the blue also tends to scatter, which is why the sky is blue. Okay, what happens to the ultraviolet?
We get sunburned.
Yes, but only partially, because some of the UV only makes it down to like here. So only a small portion of the UV gets down to the surface. How about
Some gets
X-rays?
reflected, some gets absorbed.
Yep. Okay. How about X-rays? What happens to the X-rays?
Absorbed.
Typically absorbed. Thank goodness. Why is that? Why is it good that the X-rays get absorbed?
They're damaging.
They would be, yeah, they would basically kill us all. A combination of ultraviolet and X-rays would exterminate life on Earth. Okay. How about the radio waves?
They make it down.
They make it down, yeah. And how about infrared?
Some of it comes down.
Yeah. How do we feel that?
In the heat.
Yeah, that keeps us warm. Okay. So we are really lucky in a lot of ways because the X-rays and ultraviolet rays, for the most part, get blocked by the atmosphere. However, they don't just get blocked. What we're going to do is we're going to draw this very simplistic model over here. What do we have?
An atom.
We have our atom. Okay. Now, our atom has a nucleus, which is protons and neutrons, and it has electrons flying around the outside. We're not going to get into Heisenberg and discuss, the Bohr model of the atom and different energy valence shells and different patterns of electron orbits and what it really looks like based on spin. But anyway, it's important to note that electrons have a negative charge, and they're also flying around the outside. Now, due to something called quantum theory, every electron can only exist in a certain number of energy states. As it turns out, some of the sunlight that comes down to Earth has enough energy to take an occasional electron, if it happens to collide with it, and do this. Make it pop completely out of the atom. It has enough energy that it takes that electron and makes it completely jump out of the atom. This atom now has a net positive charge, and the electron now has a negative charge, and it's floating around in space. This is called ionization, and it leads to this layer of our atmosphere being called the ionosphere because it's full of ions, ionized atoms. We basically have oxygen and we have nitrogen in various different combinations, O2, N2 typically. Sometimes we might have atmospheric oxygen, not typically atmospheric nitrogen. But once these become ionized, then we have electrons floating around. Now, so we end up with these electrons floating around in space. What are radio waves? They're a form of what? Magnetic radiation. So it makes sense that what happens is that if the level of ionization, because they're electromagnetic waves to begin with, is enough at a certain level, these will either get absorbed or potentially bent or re-emitted, depending on the mode of operation that you're doing, and will now cover a distance. Right? This is known as skip. It's called ionospheric skip. These are typically true for the high frequency bands. Now, interestingly, what do you think happens from day to night? What's the one fundamental thing looking at this picture that changes from day to night?
Temperature.
Yeah, but I mean, yes, but why? What?
The sun.
Sun just disappears.
Yeah, the sun basically, if you're on a certain point, the sun comes across, makes its travel, and then disappears. So what happens to the level of ionization as the sun moves across the sky?
Dissipates.
It builds and then it dissipates. It actually makes a track around the Earth. And what ends up happening is that the higher propagation, higher levels of propagation that require a lot of electrons up there, a lot of ionization, will basically follow the sun. What happens to all the electrons that have been ripped apart from their atoms at night? What do you think? Remembering that opposites attract.
They go
They
back
get
to
absorbed by
They
the
go back
atoms.
together. Yeah, they pop back together. So during the day, you have a lot of electrons, and at night, you have a few that haven't made it back home yet. This is a cycle that repeats over and over and over every single day. The other thing is that right under the sun, you actually have a lot of ionization in this layer called the D layer. These are labeled D and E and F. F is actually broken up into F1 and F2. The D layer builds up a lot every day when the sun is directly overhead. This is why our AM radio stations can't be received far away during the day, just because of this D layer absorption right there. It's so dense that radio waves go up into it and get absorbed. All the energy gets absorbed. And typically, the higher the level of ionization that occurs, the greater the density of electrons that are floating around up there in space, the higher the frequency that can be reflected back down. So that tends to build during the day. So in the early afternoon, late afternoon, you still have a lot of electrons floating around overhead. You're going to be able to operate on higher frequencies on the HF bands. As night falls and you get over to this side and your layers and your levels go down, well, fortunately, this D layer stuff dissipates and you're able to use lower and lower frequencies. So we call this area the daytime bands. And this area over here is the nighttime bands. And what ends up happening then is you look at your chart and you look over here and 10 meters, 12 meters, 15, 17, those are daytime bands, higher frequencies. 20 meters, 30, 40, 80, those are your nighttime bands, 160. And it changes, it swings back and forth during the day and then into night. The other thing that's cool about this is that the sun goes through 11-year sunspot cycle. Typically, when the sun is generating more sunspots, it's generating more ionizing radiation. The more ionizing radiation that is being thrown at us on Earth, the higher the frequencies that can be used. So right now, 10 meters, 12 meters, 15 meters are actually really very good during the day. 5 years from now, when we're at the bottom, we'll be lucky if we ever even see 17 meters alive during the day. And that's just the way things are. That's what physics and astronomy gives us. All right, so now at some point we're going to get back to all that. But what we're going to do is, if anybody is curious, in the book that was sent out, we are going to be on page roughly. Let's see, amateur ham radio, blah, 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 electrical principles. All right, so we're basically at the beginning of the book. I have this as page 4. So I'm basically going to be following along with this. We're going to start by drawing this thing again. What is that?
An atom.
An atom. Okay. Not
I
the
was going to say the moon.
Yeah, not J.J. Thomson's plum pudding model. This is the Bohr model. So our electrons are flying around the outside, and our protons and neutrons are stuck at the inside. So this is an atom, and it has electrons flying around the outside. Depending on what the number of electrons looks like, and whether or not these electrons can easily see all the protons in the center, protons are positively charged, electrons are negatively charged. They tend to attract each other. Depending on the degree of shielding that occurs between the electrons and the nucleus, these electrons on the outer shell, known as valence electrons, may be really easy to take away or really, really hard to take away. Current is movement of electrons. That's what it is. That is what current is. The movement of electrons. So if I have an electron and it moves from place to place, that is an electrical current. Just like water flowing through a creek. If, let's say, somebody builds a dam right here, big earthen dam, and blocks my stream, what happens to my current?
Goes up.
Well, no, it just stops. That is a resistance. It is a resistance to flow. Now, if I wanted to somehow make those electrons flow across that resistance, I would have to push really hard and get them over the top so that it could flow over the top. This amount of push is known as voltage. It's also known as electromotive force. And why is it electromotive? If you take that word, electro, electrons, and motive, to move. So that is the force needed to make electrons move. That is called our voltage. These are different symbols. These have different names. Voltage is measured in volts. Current is measured in amperes. It's also given the letter I for an impulse. Voltage is often used the letter E for electromotive force. And resistance is R for resistance. And it's measured in ohms, named after Georg Simon Ohm. Amperes are named after Ampere, who was a scientist. Volts were named after Volta. So, you get in early, you get units of electricity named after you. Good rule of thumb, right? Okay, so now what we're going to do is we're going to take an electron and we're going to try to push it into an atom. If there's an atom here that has electrons that are only loosely coupled, loosely bound, this electron on the outside that you see right here, it may or may not, want to stay in that atom. And it might be really easy to push an electron in. And then if you push an electron in, this other one will pop out as if, okay, we replace an electron with another electron. No big deal. Everything's fine. So this atom would be called a conductor. If electrons can be pushed in and another one pops back out really easily, that is a conductor. So what are some examples of a conductor?
Copper wire.
Copper wire, yeah. Other things?
Any metal.
Gold.
Gold. Yep, gold's a good one.
Silver.
Silver, good one.
Water? I don't know.
Hold that one for a minute. Other ones?
Glass.
Mercury.
Mercury is a good one. A little dangerous to use, but other ones? We're
Mhm.
forgetting one big one.
Air.
Aluminum.
Aluminum. Okay. So anything that can allow electrons to flow easily, it's called a conductor. So let's get back to that curious question of water. All right. What is water's molecular structure?
Hydrogen and oxygen.
Hydrogen and oxygen. The hydrogens are at about 109-degree angle to each other.
Looks kind of like Mickey Mouse.
It does look like Mickey Mouse. Okay. Now, oxygen is actually a slightly negatively charged thing. Hydrogen is slightly positively charged, but then the oxygen pulls the electrons away, kind of, and you end up with a slight positive charge on this end and a slight negative charge on this end. So what you end up with at that point, it's a polar molecule, and you end up with a plus and a minus, and they tend to attract each other. This is why water has surface tension. This is why it pools up in a little puddle on your tabletop. But there's not enough to make it a good conductor. So unfortunately, every so often we hear about people getting electrocuted, right? When there's a lightning strike on water. Why?
Only if there's a salt or something in the water.
There you
Or an
go.
electrolyte.
There you go. Okay. Because water itself doesn't conduct electricity very well. But if I were to take that water, and here's my H2O, and here's some H2O, and I dissolve this.
Sodium.
What is that?
Sodium chloride.
Yeah. So this water is now what?
Salt water.
Salt water. Okay. Now I now have ions in there. And if an electron happens to fly in, it will probably find a way to come out somewhere else. That makes salt water a good conductor, which is actually really important for radio because in addition to destroying copper wire, it also makes a really good ground plane for antennas if you happen to be at salt water at the beach. It's a very good conductive surface. So salt water is a good conductor. Deionized water is a very bad conductor. So now, other things that are good conductors. This is a great conductor. Anyone know what that is?
What is it?
Al.
Aluminum.
Aluminum is a fabulous conductor. But
Or as the British would say, aluminium.
But why don't we use aluminum as much as copper? I mean, it's lightweight. It's a little more brittle, but why don't we use copper? Why don't we use aluminum?
Can't take the heat.
Oxidizes.
It oxidizes. Yeah, it's very reactive. If you can keep it from oxidizing, it's great. But what happens is that the aluminum forms a thin layer of aluminum oxide, which is kind of a sort of like a gray, dull color on the outside.
An insulator.
And it's an insulator. Right. So if you take two pieces of aluminum wire and you put them together, and I know there was at least somebody who has some experience with being in New York, which is not far from New Jersey, and you take a piece of wire like this and another piece of wire like this, and you use a wire nut and you connect them together like this under a wire nut, and you rotate it and try to squeeze them down and make a connection so that you can distribute power in your house. and this is aluminum wire. Bruce, do you know what happens?
No.
How about
No.
other Bruce at North Coast? What happens, Bruce?
When we use a wire nut on aluminum wire,
Yes.
corrosion must have something to do with it.
Yes. What happens is if you live in the state of New Jersey in the 1970s, you burn your freaking house down. Because what happens is you get a high level of resistance in this wire nut because you have aluminum and aluminum, but you really have aluminum oxide in between them, which is a high resistance, and you're trying to put power through it, and it generates a lot of heat and it burns your house down. This was something that was tried in New Jersey in the 1970s. The problem was that they didn't really have airtight solutions. It works fine if you can keep it from oxidizing.
Yeah, it wasn't just New Jersey. There were other places where you can find that stuff.
Yeah, well, I mean, I'm sure there are, but like they built whole neighborhoods.
Yeah,
that all the wiring had to be ripped out. So, and I
did grow up in New York too, so
yeah. Okay, so now we're going to draw our atom again. Okay, so now we're going to have our electrons like that. Tries to push an electron in. Try to get one out the other side. So let's say that this is an atom that every electron is in there pretty happily. Right? Every electron is pretty tightly bound in there. You try to push one in, and all that happens is it gets pushed out the other side. It's pushed right back out. Another one comes in over here, and it pops right back that way. So clearly, you are unable to get electrons to flow through this material. The other one was a conductor. This is known as an insulator. The degree to which something is a conductor or an insulator is an intrinsic property defined by what's happening in its atomic structure. And again, it's measured on the extrinsic basis, like on the outside. It's measured by this unit called resistance, which is measured in ohm. That's its ability to fight the flow of current. So now what we're going to do is we're going to take our newfound knowledge of that, and we're going to make a first circuit. A circuit is comes from the word circle. That means a complete loop. And here we go. We're going to have a source of electricity. That's a battery. Here's a resistor. We're going to have an E for our electromotive force. It's going to be measured in volts. We're going to say that it's 10 volts.
So which side of that, if that's a battery, which side is a positive and negative?
Ah, yes. I'm almost there. Now we have to complete the loop.
The long side is positive, short side is a negative.
The long side is positive and the short side is negative. But now look what you made me do. Which side does the current by convention flow out of?
Positive.
Positive. What do we know that current is the flow of?
It's the flow of electrons, so it actually comes out of the negative side.
Yeah. Current is the flow of electrons. So, but we just said that our current flows out of the positive, right? Isn't that wrong?
Yep.
Let's hear from somebody who's not an engineer. Isn't that wrong?
Yes.
What do you think? It's totally wrong, right? Completely wrong. This was a mistake made 200 years ago. And by the time they figured out that there was a thing called an electron that had a negative charge, there were too many people who knew everything about this and how current went that it was too late to fix it. Our current is measured out of the positive terminal. Our actual current flow comes out of the negative terminal because we know now that it's made of electrons. But for the sake of those of you in school, for the sake of those of you doing any electrical calculations from now on, you're just going to forget that this mistake happened because it's too late and we can't go back. So current is measured out of the positive terminal.
By definition.
By definition. The other thing is that we have this thing called a ground. Ground is by definition 0 volts. That is the definition of ground. It is a reference point for a circuit. So as we go around the circuit, we are at 0 volts here. We go this way, we gain a potential because electromotive force, that's also known as a potential. We're up to 10 volts right here. How about going through the resistor? We're doing work, which causes us to lose some of our voltage. And since that is at the same point as this, we're at 0 volts right here. So we are at 10 volts right here and 0 volts right here. Go ahead. Was there a question? Okay. So now what we can say is by something called Ohm's law. This is Ohm's law. This is one of the other fundamental things that we need to learn. That E, which is electromotive force, is equal to I, which is the current flow, times the resistance. Whether you're in physics or chemistry or any or engineering, Ohm's law is really important. And I can say, having worked in industry for the last 25 years, building machinery and debugging stuff, this represents 90%. This represents and solves 90% of the problems I come across. Virtually everything that goes wrong is somehow attributable to or can be solved by Ohm's law, which is really quite daunting when you start thinking about it. I mean, it's so basic and it represents 90% of everything that goes wrong.
I would say 90% in building satellite and rockets as well.
Seriously?
Yeah, oh yeah, absolutely. When
Is it
something
like,
goes wrong, it's Ohm's law.
like a loose ground or
Yep. Or too much current through something, or power dissipation, or yep, all that. It's really true.
Okay. So E equals I times R. We can draw this as a circle. It works the same way. E equals I times R. You cross out the one you don't know. If you don't know the voltage, this just turns into a multiplication.
E over I and R.
Yep. If you don't know your current, for instance, then you have a division bar. It's I divided by R.
Hey, Scott?
Yeah.
Just a question. Why is it E equals IR and not V equals AR?
Because this is just one of those conventions. It's short for electromotive force.
Measured in volts.
Measured in volts. You could also say this is V because it's the voltage.
Right.
And I is measured in amps. That's current. And R is resistance. And that's measured in ohms. Okay, so we're going to draw our little circuit right here. And now we're going to solve it. Here we go. Somebody pick someone pick a resistor value for me.
10.
10. Okay. This is now 10 ohms. Okay. Glad you picked something easy. Okay. We have around the circuit. we have 10 volts, we have a 10 ohm resistor. What's the one thing we don't know? Here's the hint, it's in red. We don't know our current. Cross it out. I is equal to E divided by R is equal to 10 volts divided by 10 ohms. A volt per ohm is also known as an amp. That would be 1 amp. Now, that means that we have 1 ampere of current flowing through every point in the circuit. This is actually about 10 to the 18th electrons every second. A lot of electrons. It takes a lot of electrons to make an amp. Everyone know what scientific notation is yet? Everyone good? What 10 to the 18th power is?
Tera, right?
Oh no, way beyond tera. That's that many electrons per second. And that's why we don't do that. That's why we use ampere. It's a measurable value. Okay, so now that we have that, we can say how much work is being done, how much energy is being released. We now have our second version of Ohm's law. So we had a relationship between voltage, current, and resistance. Now our other one is power.
Current.
P is equal to I times E. And why is this one important? Power is measured in watts. Also known as big W. A watt is a joule per second. A joule is a unit of energy. Therefore, a watt is a unit of energy burned up or created or moved per unit time. This is actually really important because it also represents amount of work being done. Electricity can do work. We can make electricity do work for us. So now let's take our circuit and figure out what the power is in that resistor. We have 1 amp flowing times 10 volts is equal to 10 watts. So we now have 10 watts of power being burned up in that circuit. And when I say burned up, I mean quite literally burned up. What does a resistor do? It resists the flow of current. How does it do that? If any does flow, it turns it into heat. That's right. And that's why Andrew was saying that Ohm's law solves a lot of problems. Power dissipation. You have a resistor in place and it suddenly, has anyone ever seen what happens if a resistor dissipates too much power?
Magic smoke gets let out.
It lets out the magic smoke and you get a little puff of smoke. And sometimes if you're unlucky, it'll turn like kind of like red and then orange, then yellow, and then white hot and let out a big puff of smoke. I had that happen in the field once. It was a lot of fun. So this is where
because energy,
that's right.
Energy cannot be created or destroyed. It can be only be converted from one form to another.
Exactly. Did everybody get that? Energy can neither be created nor destroyed. It can only change form. So I took, in this particular case, we're going to look up at this circuit over here. And we have coming out of this resistor, what's being generated by the resistor?
Heat.
Heat. Okay. That is a net.
These are 10 watt
That
resistors.
that is a net.
Watt resistor is a big, heavy
Yes,
thing.
but let's say that is
It's
we have
warm.
10 watts of heat being generated by the resistor.
That's a 1
Where
watt, teeny weeny.
where is that energy being sourced from? Where is it coming from?
Battery.
The battery. The battery is the source. So, because it's a closed system, it is creating or delivering 10 watts of energy or 10 watts of power, 10 joules per second, and the resistor is dissipating it. So, what was the battery's energy source to begin with? What do you think?
Everything comes from the sun.
Yeah, but beyond that, but like if you have a car battery, what's a car battery's so what's a car battery? How does it store energy in a car battery?
It's a chemical reaction.
It's a chemical reaction. You have energy stored in a chemical reaction, just waiting for something to happen. That waiting for something to happen is that it gets hooked up to this resistor and it gets converted from chemical into
electrical,
which then converts into heat. And because it's not perfectly efficient, there's some losses along the way usually, but basically this is how electric motors work. If I were to replace that resistor right here
motor
with a motor, if I were to replace that resistor with a motor, what would my energy come out as?
Rotational force.
Yeah, movement.
Yeah.
If this was a motor that was spinning a shaft and this shaft had a rope on it and it was connected to a bunch of pulleys and down here there was a weight, what would it do to the weight?
Lift it.
It would lift it. It's doing work. Power is this really cool thing. This whole energy transfer thing is really awesome. What radio is, what we're going to cover is the fact that instead of a motor there, what are we going to do?
Antenna.
We're going to use an antenna and we're going to make electrons move back and forth. And in the process of moving back and forth, what they're going to do is they're going to make radio waves launch into space with energy. Isn't that cool? All right, how about a 10-minute break?
That is pretty cool.
It is pretty amazing, really. All right, so back at 11:30.
Yeah, so
was gonna say it looked like the cat got loose on the whiteboard.
No, now I'm just having fun. I figured out why it would do those dots.
Oh, why is it doing that?
Well, because it thinks my finger is a pen.
Oh, has something to do with current, probably.
Probably so.
I always wonder why those stylus work, on iPhones.
Well, I think it's a capacitive screen. Gonna get to that.
Good.
All right. Is everybody ready? Questions before we go on? Speak now. Nada. Nada. Okay. Well, so
You're not very loud.
Oh, here we go. Is that better? Make sure I got the right microphone done.
No.
Can everybody hear me okay?
5x5 here.
I can hear you just fine.
Yeah.
Hello.
Loud and clear.
Yep. Okay.
Yep.
All right.
Gotcha.
Here we go. So what we're going to do now is we're going to draw a time graph of voltage. So voltage versus time. And we're going to take our classic old battery from our car. Here's our old battery from our car. And this is a 12-volt DC battery. So that's 12 volts direct current. Current's always flowing in the same direction. Around like this and around through whatever circuits and back to here. So if I were to draw this voltage on this graph, this would be 12 volts. And what would it be 5 minutes from now? How many volts? 12 volts. How about an hour from now? Assuming it didn't go down.
12 volts.
12 volts. This is known as DC because if I have a circuit that has a resistor in it, it has current that only flows in one direction. This voltage generates DC. This is a DC voltage, and it generates a direct current. Current only in one direction. But now, what if I were to take this voltage that I drew here, and every so often I would flip this battery's direction and make it look like this, where the plus was near and the minus was down there. And my new voltage looked like this. Is that DC anymore?
Nope, you're AC.
It's ugly, right? This is known as a square wave. But it's now changing direction because when the battery is reversed, my current is now flowing this way. The current direction is backwards. This is known as AC, or alternating current. Always in one direction is DC, and now I've just made AC. Now, I could make AC that looked like that, but it turns out that it's really kind of ugly for a lot of different reasons. But there are some other things that we can do. So let us say that we have let's say we have something that looks like this. Here's a cliff. We have something that looks like water. coming over the cliff. And I put a wheel here, where it has a bunch of catch pans. What would that be called?
Water wheel.
A water wheel. Okay, excellent. Now I take this and attached to the shaft of this water wheel, I use a motor. I connect a motor to it. And now, when the water wheel turns, what happens to the motor?
Motor turns.
Motor turns. And now I connect those. What's inside here is a coil of wire that's turning inside of a couple of magnets. And as this moves, it generates a voltage and a current. And by having it rotate through there, I actually can generate, because it's rotary motion, something that looks like this. What is that called? Everyone remember what that's called?
Sine wave.
That's a sine wave. And it has a nice pure frequency. Whatever that frequency happens to be. If it does this 60 times every second, what is my frequency?
60 hertz.
60 hertz. Anybody know what the wall voltage is in your wall?
60 hertz.
60 hertz. What we have in our wall is voltage that does this 60 times every second. And it goes this way, and it goes that way, and it goes that way, and it goes that way. And changes back and forth, back and forth. It makes one full cycle 60 times a second. This is the frequency of our wall power. It could be driven by by a water wheel. It could be driven by a steam turbine. It can be driven by a whole bunch of different things. So, what is this process an example of? Converting energy. This would be kinetic energy into electrical energy. So we can take electrical energy and make kinetic energy by running a motor. We can also run it backwards and take the kinetic energy of the moving water and make electrical energy out of it. Energy's pretty cool, right? Do all kinds of neat stuff with it. Okay, so now that we've established that we can make, by changing the speed of the motor, we can make a different frequency. If we run the motor faster, we could make a higher frequency. Typically, we don't want to do that because our power grid operates at 60 hertz. But now what we have is this voltage that goes like this, back and forth, back and forth, back and forth. So this brings us some challenges. What if we have a resistor that looks like this? How do we do our Ohm's law calculation on that? Well, let's say that this is our 10 ohm resistor, and we were going to use a battery. Didn't draw a very good battery there. We're going to draw a 10-volt battery. And what we end up with is 1 amp of current and 10 watts of power. So now the question is, can we take this battery and replace it with something that sometimes power goes, oops, I don't even know what that was. Sometimes our current goes this way, and sometimes current goes this way. That still gives us 10 watts of power. I bet I could. I could use a battery and I could flip it back and forth so that the voltage looks like this. But there are lots of other problems when you do that. As it turns out, when you do something called a Fourier analysis on a square wave, it has all kinds of harmonics. It's an absolute mess to deal with. So we don't do that. But what we can do is we can have somebody, for instance, deliver us a sine wave at 60 hertz or at any frequency for that matter. And we can actually pick the amplitude of this sine wave, which is its bigness, so that if we look at how our power formula works, what's the formula for power again?
Equals I times E.
P equals I times E. Everybody memorize these and do the pi. It literally looks like a pi. P equals I times E. Now, this is true not just when we do our big calculations, but this is true all the time, at any time. So what we're going to do is look at this voltage that's coming in, which is a sine wave. And in particular, I want to look at this spot. This is a measure of our voltage. What is our voltage right there?
10 volts.
Right here?
0.
It's 0. So P equals I times E. What's our power right there?
0.
0. That's a problem, isn't it? Well, okay. Let's pick another spot. Let's pick right here. What is it right there?
0.
0. Uh-oh. How about right here?
0.
0. Uh-oh.
There's a theme.
So, well, if we want the average to be 10 watts, what does that mean? That means that to make up for all those zeros, we've got to do something, right? Uh-oh. It's got to be bigger than 10 volts in order to make an average of 10 watts over that whole time. This is actually something called RMS voltage, or root mean square. And what it is a voltage, an AC voltage that generates the same amount of effective power over a period of time as a DC, an equivalent DC voltage. It's very important. You don't have to know it beyond this, but it's good to know that when you're measuring voltage right there, if you have, let's say, 120 volts AC, that's what's in our wall. So let's say this is 120 volts AC. You will actually go all the way up to 170 volts and down to negative 170 volts. And the reason that that is true is because it generates the same amount of power as a 120 volt DC voltage. So this is AC RMS. And if you want to go into it, we can do the calculus on it. It's not overly complicated, but it does involve integration. But this is where it comes from. Anyway, so when you see something that's an RMS voltage, that's why it says RMS. And for a sine wave, it's actually square root of 2 times the nominal. Again, it comes out of the calculation. Okay, so from now on, it does not matter if we're talking about AC or DC. We're just going to refer to 120 volts is 120 volts. We're just going to say 120 volts is 120 volts, and 10 volts is 10 volts. And I don't really care which one it is. They basically, it's either DC or AC RMS. Doesn't matter. But that's where those are a little bit different. Okay, now one place that it does matter a little bit, however, is the fact that we're now going to draw our circuit and we're going to have this sine wavy thing in the power supply. This goes into a resistor. And we close our circuit. And if I were to look at the current and voltage that are generated here, if the voltage looked like this, what would the resistor see? What would the resistor do? Does the resistor care which way the voltage is and which way the current is flowing?
No.
Does not. However, what if I did something that looked like this? And I put two giant metal plates right here.
Have a capacitor.
And these are neutrally charged. They have a neutral charge. And for that period of time, when my battery, well, I don't know why it did that. Geez, did it again. There we go. So when it's positive, like this, I have a plus here and a minus here. Now we're going to start looking at individual charges. So what charges come out of the top of the battery right now? Pluses or minuses?
Plus, positive.
Okay. What charges come out of the other side of the battery and end up on the other side of this plate?
Negative.
Negatives. Okay. Now, what we're going to do is nothing more right now. We're just going to leave this. What would happen if these are at capacity? In other words, we have no room for any additional charges. What would happen?
Discharge.
Has nowhere to go.
Current stops.
It stops. Our current stops. If we were to try to measure the current, we would see that the current would now be zero. But what I'm going to do now is I'm going to take this and I'm going to flip the battery like that. So our plus is here and our minus is here. What's going to happen to the plus charges that are accumulated on that one side? Is that they are now going to flow back to the negative terminal of the battery, and the negative ones are going to flow back to the positive terminal of the battery. Eventually, there will be nothing there, and it will be neutral. But what happens if we leave it for a little bit longer? We have now replaced one with the other, and now we have negatives here, and we have positives over here. Until what happens?
Flips the battery again.
Until you flip the battery again, because now it's full and there's nowhere else for it to go. Then you'd flip the battery again. If you flip the battery and you switch it to this, pluses, minuses, these flow this way and these flow this way until you have nothing. And then eventually those are gone. And now the direction of flow is that way, and the pluses are here, and the minuses are here again. And then it gets filled up. How long could I go on doing this? Yeah, I could go on doing this forever, right?
Gee, it looks kind of like an AC wave.
It does, doesn't it? Mm-hmm. This device is called a capacitor. And It's measured in farads, big letter C for capacitance, measured in big letter F for farads for Michael Faraday. Typically what this is literally two big metal plates with a dielectric material in between them. A dielectric is an insulator. So we talked about conductors. What would be something that doesn't conduct electricity?
Paper.
Hmm?
Paper.
Paper. What else?
Wood. Well,
Wood.
Air.
Yep. Air. Yep. What else?
Oil.
Oil. Yep. I saw
So
someone say glass, other things. Mica.
Stone.
Mica's rock.
Rubber.
Yeah. Rubber.
Plastic.
Ceramic, Teflon. Yeah. Now we're getting answers. So basically all these things that don't conduct electricity well could be used as a dielectric to fill the gap. Their ultimate goal is to make sure that whatever voltages form on these two sides, they are able to withstand the amount of voltage that's there without arcing through. If it arcs, it doesn't do very well. Again, this is called a capacitor. And now if I have all the pluses on one side and all the minuses on the other side, what are they trying to do?
Get to each other.
Because
Their energy.
that's right. Positive pluses and minuses attract. So what is the only thing keeping them from doing that?
The insulator.
The insulator and the space in between the two, the physical device itself. They are actually exerting a force, and the insulating material is exerting an opposite force to keep them from flying together. So this is known as an electrostatic force. They're static. They're trying to make things move, and they can't because they're being held apart. By doing that, by creating an electrostatic force.
And it sticks to you. That's the electrostatic force.
Oh.
So the fact that there's now an electrostatic force, an electric field in between them, we are now storing energy in an electric field.
In a capacitor.
A capacitor stores energy in an electric field. That is a capacitor. Now, the other interesting thing about a capacitor is, remember what we drew up here? And every time we switched the battery, it discharged and recharged the opposite direction. Right? Everybody remember that? Well, what is the act of flipping the battery equal to? What kind of current is that?
AC.
Is it possible to do it fast enough that the capacitor never really charges up? What do you think?
Yes.
Mm-hmm. If the capacitor never really charges up, does the battery know that it's even there? What do you think? If it never really charges up and you never really break the flow of current, does the battery even know that the capacitor is there?
No.
No. And in fact, at AC, a capacitor looks like a short circuit. If I were to make it DC and make it so that it was always in one direction, like this, the capacitor would charge up. And then would anything else flow? Nope. What does it look like?
An open circuit. Yeah.
That looks like an open circuit. So now we have a device that behaves differently depending on whether AC or DC is connected to it. Now we're going to add another one, which does something similar to it, but different. is called an inductor. The letter for inductance is the big letter L, and this is measured in henries. Big letter H. So if a capacitor stored energy in an electric field, an inductor is its analog. If we draw a piece of wire and we have a current flowing through it, there will be a magnetic field that is generated around the wire. If we were to put two wires next to each other that have a magnetic field that repel each other, they would actually jump apart. If they were opposite magnetic fields, they would attract each other. This is a process called induction. And what ends up happening is that this is a magnetic field and it occurs in circuits, loops in space around the wire. And it's defined by the right-hand rule. If you hold up your thumb and then roll your finger, it has to be your right hand. Hold your thumb out. That's the direction of current flow. You roll your fingers over. That's the direction of the magnetic field being generated. If I were to do it and roll it so that my wire was wrapped in a coil like this, it would actually end up looking like this. My magnetic field would end up looking like that. And if you've ever seen like pictures of solar prominences coming out of the sun and stuff like that, those are magnetic field lines, and they actually look like something like this. And where they break is where we get solar storms. Anyway, storage of energy in a magnetic field. One thing about this is that if a magnetic field exists, it doesn't like to be broken. So if I suddenly were to, let's say, if I were to hook this up to a battery like this, plus minus, I would get current flow. I would generate a magnetic field. And what would happen after that? What do you think? What would happen?
Eventually the battery would wear down.
Eventually the battery would wear down, but if I had an infinitely powerful battery, it would just go on forever. For DC, an inductor looks like a short circuit. Current just keeps flowing, magnetic field keeps being made, the energy is stored. How about if I were to try to switch this and momentarily disconnect it? What do I have left? What do I have? I have an inductor sitting there in space with a magnetic field that is now in the process of collapsing because there's nothing left to support it. The capacitor, when I drew a capacitor could store energy in pluses and minuses. Are there plus and minus particles for magnetic energy?
No.
Yes.
Well, not that anyone's ever discovered. That'd be a magnetic monopole, and those don't exist. So you have all this magnetic field energy, and what has to happen to it? It's got to go somewhere.
Bless you.
Thank you. So now it's an open circuit. What happens was that this was plus and this was minus. Now it reverses and says, well, I've got all this energy I've got to get rid of. It says, I'm going to make this minus and this plus, minus, plus. And until it can get rid of that energy, it builds bigger and bigger and bigger until what eventually happens? I have a physical gap.
You get a burst of energy across that gap.
Well, against this gap, you have a big minus and a big plus, and this might be 20,000 volts.
It'd be an arc.
You get a big flash. Yes.
Is this how a strobe light works?
Essentially, this is how a an ignition coil works in a car.
In a car.
So, an AC for this is AC. Inductors are very unhappy when it comes to AC for the most part. They're a short circuit for DC and an open circuit for AC. Now, this is taken in the extreme because it turns out that inductors are not completely unhappy in the AC world. And in fact, if you can make them happier, you can do pretty cool things with them. Like I can do something that looks like this. Tell me if anyone knows what this is.
Microwave oven.
Yeah, there is one of these in a microwave oven.
Yeah, it's a transformer.
That is a transformer. So if I have side 1 and side 2, let's make it the right color. And when I have AC or DC or anything flowing through side 1, what does that make going through that coil? A wire going through a coil makes what? What kind of field?
Magnetic.
Magnetic. So that makes a magnetic field, which now flows through here. Well, what happens when it gets to the other side? This is a core which is very, very happy with magnetic fields flowing through it. It's called a ferromagnetic core, usually iron or steel. What happens when it goes through that other coil? If a current makes a magnetic field makes a current. So I put power in on the left side, and because energy can neither be created nor destroyed, what comes out on the other side?
Power.
I get power out on the other side. And what's really interesting is this is the number of turns, N1, and on the other side is N2. These do not have to be wrapped the same number of turns. If I have a ratio of 10 turns on this side to every 1 turn of wire on this side, my voltage ratio will be 10-1. So if I have 120 volts AC over here, what do I get on the other side?
12
volts.
Yep. That would be a step down transformer. If my ratio instead were 100 to, let's say, 1,000.
10,000.
Yeah, I'd have 120 coming in.
Oh,
and I would have
12,000. Would it be?
Yeah, 12,000 volts coming out the other side. Where would I ever want to see something like this? And here's a hint. You have one near your house.
Power utility poles.
Utility poles. Look up on the utility poles, and you will probably see a 12,000 volt transformer on one side, and usually it's 240 or 480 on the other side.
Another fun example are the neon signs, the old school ones, not the new LED ones, but the old neon sign, those tubes have a transformer like that.
Yep. So what would be the purpose of this? So now we're going to get into something which is an impact of Ohm's law. So what we're going to do is we're going to make a power station. And here's your house. Little chimney and doorway, and here's a window and a window. Car parked out front. Okay. And in between, you've got these transmission poles. And this connects to here, connects to here, and eventually connects to your house. And let's say it's not just one house. Let's say it's 10,000 houses. Each house is consuming 1,000 watts of energy or 1,000 watts of power. Okay, here we go. You know what? Let's just make it 1,000 houses. We'll make it a little easier to calculate. Okay. What is the total power consumption by all of these houses?
Oh, that'd be
1,000 times 1,000. 1 million watts. Okay. Energy can neither be created nor destroyed. So what we're going to do is we're going to figure out how much power is being delivered by the utility. If we have 1 million watts being used, how much is being delivered? I hope it's 1 million watts, right? Okay. So what's the equation for Ohm's law for power again? P is equal to what?
I times E.
All right, everybody. P is equal to I times E. Super important. Okay. What's the other form of Ohm's law? E is equal to what?
I divided by R. IR.
And Bruce knows this, everybody.
Yep.
E is equal to I times R. Okay. So what I can do here is I can actually substitute something and I can rearrange the bottom equation and I can make this P is equal to E squared divided by R. I could also make it I squared R. So I could rearrange my top equation so that it's either of those. So now what I'm going to do is say that for example number 1, I'm going to take a voltage of, let's say, 100 volts. By P is equal to I times E, how much current would I have to bring through there? How much power is total in there? 100 million watts. So my current would be 10,000 amps. Everybody agree with that? Okay. Here's where it gets really fun. I promise this is fun. This is the definition of fun. We're going to now look at these power lines as a big old resistor because everything has resistance. And these, as a group, have a resistance of 0.001 ohms. So what is the total power consumed because I have 10,000 amps going through that? I squared R. What is 10,000 squared?
Wow.
1, 2, 3, 4 times 0.001. This is the amount of power being burned up as heat. Ready? Does anyone see a problem here? I'm burning up 1 million watts in heat. What's going to happen to those wires?
Oof.
Burn up and fall.
And I'm only delivering 1 million watts to the customer, so this doesn't work. So obviously there's something that is impacting this greatly. That is that current, right? The current is having a huge impact on my power consumption. How can I fix that? I have to reduce my current. How do I reduce my current?
Resistance.
No, by
No.
Ohm's law. How do I reduce my current when keeping the power the same? P equals I times E. If I keep my power constant, if I reduce my current, what do I have to do with my voltage?
Yeah, they increase the voltage.
Yep. So now, let's say I want to make a big change. And instead, I can produce power at 100,000 volts. By Ohm's law, how much current do I now have to deliver? By P is I times E. I need a total of 10 amps. That's it. And what's the power dissipated in my wire now? It's 100 because it's 10 times 10 times 0.001 is equal to 0.1 watts.
Wow.
How did I achieve that? What's the one thing that we did?
Got to use a transformer.
What did we do? We made the operation at 100,000 volts. And how did we make the operation at 100,000 volts? We put in a big transformer to convert from low voltage to really high voltage. And that, when you look up in the sky, is what you see on those power lines, running very high voltage and very low current. All right, next, we're going to get to, let me just take a look here. Covered that, we covered that, covered that, covered that, covered that, covered that. Series and parallel, okay. All right, is everybody good with this so far? If you have any questions, please ask. This is a series circuit. Series means that things are encountered in series, one after another. If I have a resistor here and a resistor here, the current that is flowing has to go through both of them. You can say that the resistance total is equal to R1 plus R2. These experience the same current, but they split the voltage. That is known as series. I can also draw these as a parallel circuit. Here's one. Notice that these two wires right here are parallel to each other, thus a parallel circuit. It can also be said that the voltage here, if I have 10 volts here, well, this is a piece of wire. I have 10 volts here and I have 10 volts here, and this is ground, and ground is at 0 volts. So I have 0 volts here and 0 volts here. So each device receives the same voltage. Because they're receiving the same voltage, the amount of current that they see is determined by their individual resistances. So what we're going to do is just draw a couple of examples of such a thing. Here we go. This is one circuit you may recognize if you stop and think about it. Okay. And these are producing light. Can anybody think what that would be? And what would be the problem if one of these decided to burn out?
The whole thing would go out.
Yeah, where do you find that? What is this circuit similar to?
Christmas tree lights.
Those are Christmas tree lights. That's right. Where if you lose one bulb, you lose the whole string. Now, if I were to instead make a circuit that looked like this, it's plugged into the wall. I had a light over here and a light over here and a light over here. And one of those bulbs were to burn out, what would happen to the rest of them?
Nothing.
Nothing. What is wired this way?
Your home.
Your home. That's right. Everybody lives in one. Some kind of home with lighting, I hope. All of your things are wired in parallel. The reason is that if anything turns off, it doesn't make the rest of your house dark. It also ensures that if you have two light bulbs that are slightly different, one is not dimmer than the other and cause the other one to look weird.
Except for those old-fashioned Christmas tree lights.
Except for the old-fashioned Christmas tree lights. Now, the other thing about this is that, okay, so now we're going to say, well, let's say that somebody decides that they're going to go crazy and they're going to plug in everything that they have. All right, so we're going to plug in everything into every outlet available in your house. Okay, so long as this power supply can produce enough, deliver enough current and energy to run all those lights in your house, those lights will all light up, right? Let's say these draw 10 amps each. They're big light bulbs. Those are 10 amps each. What is the total amount of current that has to be delivered to all those circuits? It all adds together.
60 amps.
60 amps. Okay. By the National Electric Code, if I remember right, this is a, let's see, is it a 4-gauge wire? To be able to handle that much current is a 4-gauge wire. That's a big piece of wire. Well, nobody builds houses that way. The lower the number, the bigger the wire. Most houses are built with either number 10 or number 12 wire. This is good for 30 amps. This is good for 20 amps. What if somebody decided that they were going to hook up all those lights at the same time? What would happen to that wire?
Oh, the wire would melt.
Because P is equal to I times E, and E is equal to I times R, and every piece of wire has a little bit of resistance. So that wire is going to get what? Really hot. Yeah, because it turns out that power is equal to I squared R. It goes up as the square of the current. So that wire is going to get really hot. What happens if that wire is not protected and is inside your wall?
Fire.
It's going to set your house on fire. That's right. Fortunately, we have something that looks like this. That is called a fuse or a circuit breaker. This is an overcurrent protective device that when it sees that, let's say this has been calibrated to be good to carry 20 amps forever. If it sees an overcurrent, like all 6 of those turned on at the same time, it will intentionally trip, keeping your house from burning down. That's why we never go and replace like a 20 amp circuit breaker. You could probably get a 50 amp circuit breaker and put it in its place, but you'd probably burn your house down. That's why we don't do that. That's why if we build our own pieces of equipment, that's why we also put fuses in line, so we don't set something on fire or cause damage. Okay. Other stuff. We're back to circuits and components in circuits. Let me just pop this up. Series. Parallel, I want to make sure we cover all that. Power, power, power. We did that. Okay, units. You know what? We're gonna skip over units just for a second here. Decibels are part of units, capacitors, inductors. We did batteries. Okay. A primary cell is a one-time use battery, not rechargeable. That's known as a primary cell. Carbon zinc battery, that's your old battery that was listed as heavy duty, which really wasn't. That's a non-rechargeable. Lead acid, lithium ion, nickel metal hydride are all rechargeable. Lead acid is what you find in your car. So why should you never what happens if you overcharge your car battery and then or end up with a battery that's completely discharged and then try to jump it? Why should you always make sure that you don't create a spark near the battery?
Because it produces hydrogen gas.
Because it produces hydrogen gas. Everyone remember the Hindenburg? Hydrogen gas is very, very, very flammable. So a battery that's severely overcharged or undercharged can be an explosive. And what is contained in a car battery that's a lot of fun to play with?
Sulfuric acid.
Sulfuric acid, yes. So then you get an exploding battery that's showering you with sulfuric acid. So try to avoid that. Okay, diodes. We're going to do diodes. We're going to do transistors. And okay, here we go. One of the most significant things that has come about since the development of electronics, development of electrical devices is this. So we covered two different things. One is a conductor, one is an insulator, but there's something in between called a semiconductor, which is a kind of okay conductor. Usually this is made of silicon or germanium, one of those two. Silicon is a lot more common, so that's why, I mean, it's in sand. That's why we use it so much. So silicon is a semiconductor, and it's kind of conductive and kind of not. In order to tip the scales of what makes it conductive or not, we can do certain things to it. We can take silicon and we can add a few pluses, which are known as holes, or we can add a few electrons, which are your minus charges. A hole is an absence of an electron. And the way we do that is we take our silicon and we throw something called a dopant in its place. We fill it with a few extra things that either have a few extra electrons or not. This would be called a P, and this would be called an N. This is known as the cathode.
And the anode.
And this is the anode. Known for, and those come across because of cation and anion, negative and positively charged ions. So what we end up now with is this thing that only conducts electricity in the direction of the arrow, and only when it's positively biased, which means you get a big enough plus and minus here from outside to allow it to go forward. It needs a little bit of a push. Typically for a silicon diode, this is 0.7 of a volt. For a germanium diode, it's about 0.3 volts. But most of the diodes that we're going to encounter are 0.7 of a volt because they're usually silicon diodes. Those are more common. And what's important to note is if we put this in a circuit, so here's our battery. Let's say this is a 6-volt battery. If we have 0.7 volts minus whatever gets dropped here, then the current will flow around the circuit. If this voltage at the battery is too low, like 0.5 volts, there will not be adequate voltage to forward bias this diode, and nothing will happen. If we were to flip this battery so that it had really any voltage up to a certain point, at which point it can't resist anymore, and we tried to flow current backwards through it, it would not allow us to do that. A diode becomes a one-way street. Now, why might you say is this important? The reason it's so important is when we start dealing with AC. What does AC look like again? The most common form of AC is a sine wave, right? And AC looks like this as a sine wave. And when it's positive, we're going to assume that it goes above 7/10 of a volt. So for this entire section right here, which I'm going to pick a different color for, it's going to allow current to flow. And for the rest of the time, when it's not, it's going to be a brick wall. So my current looks like this. Going in looks like that, and my voltage going out looks like this.
Wow.
What is this? Is it AC or DC?
DC.
I converted AC to DC. This is exceptionally profound because this is the basis for power supply. Most electronics utilize DC. Most power is delivered to our homes using AC. It can be delivered over very long distances using AC. Not so much using DC. What we do is we generate, we have AC generated at very high voltages. We convert it down, and then we're at our actual device, we run a power supply, and we convert our AC into DC for use. This is a very basic power supply. And actually, this is really what I've drawn here is almost what you're going to get. We have to add a few things. What's that thing called again?
Capacitor.
Capacitor. And that filters the voltage so that instead of going all the way to 0, it looks like this. And then we're going to add another device, which looks like this, which is a special kind of diode called a Zener diode, which is a voltage reference diode. And then we'll probably throw another resistor in somewhere. But essentially that right there allows voltage to run up to only a certain point, knocking off the peaks, giving us a nice stable voltage. This very simple looking circuit is an AC power supply. It's the fundamental thing that runs every piece of equipment that you have, like including this for charging a phone, for running your computer, etc., etc., etc. And the center point of that is the diode. The other thing we can do with it is we can take two diodes and put them back to back. I don't know why that keeps happening. You can take two diodes and put them back to back. Make a sandwich. Or we can do this. When we lay them out vertically, we get something that looks like this. This is an NPN transistor. And what we do with this is the P. When we put a voltage here, between here and there. We get a current flow here, which opens up this enormous channel for current to flow from the top to the bottom. This gives us something called amplification. And amplification is the basis for microphones, for being able to talk to each other, for being able to generate and make things bigger. So this is the base and the collector and the emitter of a bipolar junction transistor. And in particular, this is an NPN transistor. If I were to swap it to PNP, the arrow would just point different and the current flow would be opposite. So we take a look at this, and you see in this drawing right here, device number 2 is a transistor. By putting a voltage on the base of the transistor, we turn the transistor on, which allows current to flow from that battery, which is number 4 on the other side of the transistor, through the light bulb and down to ground. So basically, by turning on the voltage on the left-hand side, we turn on a light bulb on the right-hand side. It's an electronic switch. A simple switching circuit. Any idea where something like this might get used? Try in every single computer that you have. The transistor is the transistor is the device that makes all the computers possible, all computers possible. Now, yes, it used to be true that people could have done them with vacuum tubes, but that takes a lot more space. There's another kind of transistor. Does anybody recognize what that looks like right there with 2 plates in parallel?
Capacitor.
Okay, yep, that looks like a capacitor. And how does a capacitor work? By generating an electric field in there. So this is a different kind of transistor known as a FET. Or a field effect transistor. Again, 3 terminals. If you put a voltage here on the gate, and then you have a drain and a source. By putting a voltage on this, it essentially opens up this channel for a very large current to flow. So essentially, again, giving you amplification. Now, one thing that's really important about transistors is they have multiple different ways in which they can operate. And we're going to be done in just a minute, by the way. I know we're up against the time. So if this is a transistor, it has an input and an output. Ideally, a certain input gives you a linear output, but it really doesn't work this way. It works like this. At a certain point, below a certain point, it doesn't really work so great. And above a certain point, it's full. You can't stuff any more electrons into it. So this is called the cutoff region. And this is called the saturation region. And this is called the linear region. So if we're trying to amplify something and make it a pure, larger replica, anyone ever heard of a linear amplifier? This is what we use for audio. This is also what we sometimes, depending on the mode, use for like guitar amps and things like that. The other end of things is this cutoff and saturation. If you were, let's say, doing a computer, computers are ones and zeros, right? Either on or off. All this stuff in between is sort of on and sort of off. So computer logic operates in these two regions. Because a computer likes to see either ones or zeros. This is a switching function. It's either completely cut off or completely in saturation. And that's the uses of a transistor and why we use transistors in a certain way. And I think I got to give my voice a rest. And tomorrow, we're going to be covering, we're going to be doing a few more schematics. And let's see, we're going to get into more antennas. And let's see, what else? Other devices. We're going to be doing math, or what do they, I can't remember what they're called. Resonances, integrated circuits, and then radio waves, which we already largely did today, but we're going to revisit it for propagation purposes, covering some more esoteric modes of propagation, things that don't require the ionosphere somewhat. And then again, we get into antennas and what an antenna does and why it does what it does and how to build it and what polarization is and how to feed. Notice it says feed line, antenna types, and then there was feed line. Feed line is how you deliver power from a transmitter or a receiver to the antenna that it's connected to. That's called a feed line. So we're basically getting to the point of building a radio system here. And then modulation techniques, how to get data into a radio and then out of the antenna. Heck of a first day. Comments? Questions? Please?
I have a lot to review.
So have you seen some of this before?
Yeah, I've seen some of it. I think mostly I'm unfamiliar with the schematics and the circuitry, so I think that's kind of what I need to go over.
Okay. But
I missing the first hour of this really put us behind.